Imagine, if you will, that everything you see around you, every atom in your body, every grain of sand on Earth, every star in the night sky, every galaxy stretching across the cosmic web, all of it once occupied a space smaller than the period at the end of this sentence. Not just the matter, but space itself, time itself, the very fabric of reality, compressed into a point of infinite density and infinite temperature that physicists call a singularity. Then, in an instant that defies all human comprehension, it exploded. But this wasn't an explosion in space, it was an explosion of space itself. In the first fraction of a second, the universe expanded faster than the speed of light, growing from subatomic to astronomical in scale. Temperature dropped from infinity to merely billions of degrees. The fundamental forces that govern our reality crystallized out of primordial unity. Matter and antimatter fought a cosmic war that matter barely won. And in those first few moments, the seeds were planted for every star, every planet, every living thing that would ever exist. This is the story of the Big Bang, the prevailing scientific theory for how our universe began. But to understand how we arrived at this extraordinary conclusion, we need to journey back through one of the most profound revolutions in human thought. We need to explore how humanity discovered that the cosmos itself has a history, that the universe is not eternal and unchanging as our ancestors believed, but dynamic, evolving, and filled with mystery. For most of human history, the very idea of cosmic origins would have seemed absurd. The universe was eternal, it had always existed and always would exist. This wasn't just religious dogma, it was considered the most rational scientific position one could take. The heavens were the realm of perfection, where celestial bodies moved in perfect circles according to divine mathematical principles. Change was possible within this cosmic system, but the system itself was eternal and immutable. This eternal view of the universe wasn't merely a product of ancient ignorance. It was deeply embedded in the philosophical and mathematical frameworks that shaped Western thought for over 2 millennia. Aristotle, whose ideas dominated medieval scholarship, argued with compelling logic that the universe had existed forever and would continue to exist forever. How could something come from nothing? How could time itself have a beginning? These questions seemed to lead to logical contradictions that could only be resolved by accepting an eternal cosmos. Medieval scholars, working within Aristotelian frameworks refined by Islamic and Christian thinkers, conceived of the universe as a vast hierarchy of nested celestial spheres. Each sphere rotated with perfect regularity, carrying the planets and stars in their eternal dance across the heavens. This was not just a physical system, but a cosmic symphony where each celestial body played its part in maintaining the harmony of existence. Change occurred within this system, seasons changed, planets wandered among the stars, comets appeared and disappeared, but the fundamental structure of reality remained constant. Even when the scientific revolution began to challenge medieval cosmology, the assumption of an eternal universe remained largely intact. Galileo Galilei revolutionized our understanding of planetary motion with his telescopic observations, revealing that Venus had phases like the Moon and that Jupiter had its own satellites. These discoveries shattered the idea of perfect celestial spheres and proved that the Earth was not the center of all motion. But Galileo still conceived of the universe as a vast, unchanging stage upon which these newly understood motions played out. The cosmos revealed by Galileo's telescope was immensely larger than medieval thinkers had imagined, but it was still essentially static. Stars were fixed in their positions like diamonds on a black velvet cloth. The Milky Way, that ghostly river of light stretching across the night sky, was revealed to be composed of countless individual stars, but these stars appeared permanent and unchanging. The universe might be bigger than anyone had thought, but it was still eternal. Johannes Kepler's discovery that planets orbit the Sun in ellipses rather than perfect circles refined our understanding of celestial mechanics. But it didn't challenge the basic assumption of cosmic permanence. Isaac Newton's Principia went even further, providing a mathematical framework that could describe the motion of everything from falling apples to orbiting comets. But Newton too assumed that space and time were absolute and eternal, fixed backdrops against which physical events unfolded. In Newton's universe, space was like an infinite three-dimensional grid that had always existed and always would exist. Time was like an eternal river, flowing at constant rate, carrying events from past to future, but never itself changing or having beginning or end. Matter moved through this space and time according to precise mathematical laws, but space and time themselves were immutable. The idea that space and time might be dynamic, might have origins, was completely foreign to the Newtonian worldview. This Newtonian conception of absolute space and time dominated scientific thinking for over 2 centuries. It seemed not just reasonable, but inevitable. How could space itself have properties? How could time itself change or evolve? These concepts were so fundamental to human experience and rational thought that questioning them seemed pointless. Scientists could study how matter moved through space and time, but space and time themselves were beyond the reach of scientific investigation. When Albert Einstein developed his theory of general relativity in the early 20th century, he was initially working within this same conceptual framework. The universe, in Einstein's original thinking, was static, a 4-dimensional space-time manifold that extended infinitely in all directions without beginning or end. This wasn't just theoretical preference, it seemed to be supported by all available observations. The night sky that Einstein could observe looked essentially identical to the one that had greeted Newton, Galileo, and even ancient Babylonian astronomers. The stars appeared fixed in their positions, forming the same constellation patterns that had guided navigation and marked seasons for thousands of years. There was no obvious evidence of cosmic evolution or change on any grand scale. The universe appeared to be a vast, stable system operating according to eternal laws. But Einstein's equations refused to cooperate with his assumptions. No matter how he manipulated the mathematics of general relativity, the equations insisted that space-time must be dynamic, either expanding or contracting. This prediction was so contrary to Einstein's expectations and to all observational evidence that he initially thought he had made an error in his mathematical derivations. Einstein spent sleepless nights checking and rechecking his calculations. The equations were beautiful, elegant, and internally consistent. They successfully unified space, time, matter, and energy into a single, coherent framework. They made precise predictions about planetary orbits, the bending of light by gravity, and the slowing of time in gravitational fields. But they refused to describe a static universe. The implications were profoundly disturbing to Einstein and virtually every other physicist of his era. If the universe was either expanding or contracting, then it must have been different in the past than it is today. Wind the clock back far enough, and you might reach a moment when the universe was infinitely small and dense, a condition that seemed physically meaningless. Run the clock forward, and the universe might expand forever into cold, empty darkness or collapse back into a hot, dense state, similar to its beginning. Either possibility challenged fundamental assumptions about the nature of existence. An expanding universe seemed to require a moment of creation, raising uncomfortable questions about what existed before that moment and what caused the expansion to begin. A contracting universe faced similar problems, but in reverse. What would happen when the contraction reached its ultimate limit? The mathematics suggested infinite density and temperature, conditions where the laws of physics themselves would break down. Faced with these disturbing implications, Einstein made a decision that he would later call his greatest blunder. He introduced an additional term into his field equations, the cosmological constant, represented by the Greek letter lambda. This term represented a kind of cosmic repulsion that would act opposite to gravitational attraction. With the right value of the cosmological constant, Einstein could construct a model of a static universe that neither expanded nor contracted but remained in perfect equilibrium. Einstein's static universe was an elegant mathematical solution, but it had a fatal flaw that would soon become apparent. The equilibrium between gravitational attraction and cosmological repulsion was inherently unstable. Any small perturbation, the formation of a galaxy, the explosion of a star, even the passage of a light wave, would disturb this delicate balance and cause the universe to either begin expanding forever or collapse into itself. Russian mathematician Alexander Friedmann was the first to recognize this instability when he published a series of papers in 1922 and 1924 analyzing Einstein's equations more carefully. Friedman showed that Einstein's static universe was like a pencil balanced on its point, theoretically possible but practically impossible to maintain. The slightest disturbance would cause it to fall in one direction or another. More importantly, Friedman demonstrated that Einstein's equations naturally described dynamic universes that evolved over time from simple initial conditions into complex structures. These Friedman models could expand, contract, or oscillate depending on their total energy content and initial conditions. The static universe was just one special case among many possibilities, and it was the most unstable case of all. Einstein initially dismissed Friedman's work, even going so far as to publish a rebuttal claiming that the Russian mathematician had made computational errors. But Friedman was correct, and Einstein eventually acknowledged this. The universe described by general relativity simply could not be static, it had to be in motion. While this mathematical debate was unfolding in theoretical physics journals, observational astronomy was beginning to reveal a universe far larger and more complex than anyone had imagined. The early 20th century marked the beginning of modern astrophysics, as new instruments and techniques allowed astronomers to study the cosmos with unprecedented precision and reach. One of the most puzzling features of the night sky was the nature of spiral nebulae, fuzzy, spiral-shaped objects that were visible in large telescopes, but whose true nature remained mysterious. Some astronomers thought these objects were clouds of gas and dust within our own Milky Way galaxy, perhaps in the process of forming new stars. Others speculated that they might be separate island universes, enormous collections of stars located far beyond the boundaries of our own galaxy. This debate about spiral nebulae was really a debate about the scale of the universe itself. If the spiral nebulae were nearby objects within our galaxy, then the Milky Way constituted virtually the entire observable cosmos. But if they were distant galaxies in their own right, then the universe was vastly larger than anyone had previously imagined. The resolution of this debate came from Edwin Powell Hubble, working with the newly completed 100-inch Hooker telescope at Mount Wilson Observatory in California. This instrument, completed in 1917, was the largest and most powerful telescope in the world, capable of resolving individual stars in objects that appeared as mere fuzzy patches to smaller telescopes. Hubble's breakthrough came from his study of Cepheid, variable stars, a special class of stars that pulsate with periods directly related to their intrinsic brightness. This relationship had been discovered by Harvard astronomer Henrietta Swan Leavitt through her careful study of Cepheids in the Magellanic Clouds. By measuring how fast a Cepheid pulsates, astronomers could determine its true luminosity. By comparing this to how bright it appears from Earth, they could calculate its distance using the inverse square law. Using this technique, Hubble was able to identify Cepheid variables in several spiral nebulae and measure their distances with unprecedented accuracy. What he found revolutionized our understanding of the cosmos. The spiral nebulae were not nearby clouds of gas, but enormous stellar systems located millions of light years away. In 1925, Hubble announced that the Andromeda Nebula, the largest and brightest of the spiral nebulae, was actually a galaxy containing billions of stars, located more than 2 million light-years from Earth. In one stroke, Hubble had expanded the known universe by a factor of thousands. Our Milky Way galaxy was not the entire cosmos, but just one island in an ocean of galaxies. The universe was immensely larger than anyone had previously conceived, filled with billions of galaxies, each containing billions of stars. But Hubble's most revolutionary discovery was yet to come. As Hubble continued his observations, measuring distances to more and more galaxies, he began to notice something strange about their motion. Using spectroscopy, the technique of analyzing light broken down into its component wavelengths, he could measure how fast these galaxies were moving relative to Earth. When an object emitting light moves toward or away from an observer, the wavelength of that light gets shifted due to the Doppler effect, the same phenomenon that makes an ambulance siren sound different as it approaches and recedes. Light from an approaching object gets compressed to shorter, bluer wavelengths, while light from a receding object gets stretched to longer, redder wavelengths. Hubble found that virtually every galaxy he studied showed redshift, indicating that they were all moving away from us. Even more puzzling, there appeared to be a direct relationship between a galaxy's distance and its recession velocity. The farther away a galaxy was, the faster it was receding from us. This relationship, which came to be known as Hubble's law, could be expressed with elegant simplicity. Recession velocity equals Hubble's constant times distance. At first glance, this discovery might seem to suggest that our galaxy occupies a special position at the center of the universe, with all other galaxies fleeing from us in every direction. But Hubble and other astronomers quickly realized that the pattern he observed could be explained by something far more remarkable: the expansion of space itself. To understand this concept, imagine drawing dots on the surface of a balloon to represent galaxies, then inflating the balloon. From the perspective of any dot, all other dots appear to be moving away, and the farther away a dot is initially, the faster it seems to be receding. No dot occupies a special position. Each one sees the same pattern of universal recession. This balloon analogy helps us grasp the counterintuitive concept of cosmic expansion. The galaxies aren't flying apart through static space like fragments from an explosion. Instead, space itself is expanding, carrying the galaxies along with it. New space is constantly being created between existing galaxies, causing them to move away from each other even though they're not actually moving through space. The implications of Hubble's discovery were staggering. If the universe is expanding now, then it must have been smaller and denser in the past. Run the cosmic movie backward, and you eventually reach a moment when all the matter and energy in the universe was compressed into an infinitesimally small point. This would be a state of infinite density and temperature, a condition that physicists call a singularity. But what could cause such a state to suddenly begin expanding? What triggered the moment of creation? And what existed before that moment? These questions pushed science to its limits, challenging basic assumptions about causality, existence, and the nature of reality itself. The resistance to Hubble's interpretation of cosmic expansion was immediate and intense. Many astronomers and physicists found alternative explanations for the observed redshifts that didn't require accepting an expanding universe. Perhaps the redshift was caused by some unknown interaction between light and matter during its long journey through space. Perhaps there were systematic errors in distance measurements that created the illusion of a correlation between distance and recession velocity. The idea of cosmic expansion seemed to violate common sense and physical intuition. What did it mean for space itself to expand? Space was supposed to be the container in which physical events occurred, not something that could itself change or evolve. The concept challenged the most basic categories of human thought about space, time, and existence. Even Einstein initially resisted Hubble's interpretation, preferring to believe that some unknown physical mechanism was responsible for the observed redshifts. The idea that his own equations had predicted cosmic expansion decades before its observational discovery was too revolutionary for even its creator to accept immediately. But as more observations accumulated, the evidence for cosmic expansion became overwhelming. Other astronomers confirmed Hubble's measurements and extended them to even more distant galaxies. The linear relationship between distance and recession velocity held across vast ranges of distance and velocity. Alternative explanations for the redshifts became increasingly contrived and implausible. By the 1930s, most astronomers had accepted that the universe was indeed expanding, but this acceptance raised profound new questions about the nature and origin of the cosmos. If the universe had been expanding for billions of years, what had started the expansion? What existed before the expansion began? How long had the universe been expanding, and would it continue expanding forever? These questions led to one of the first major predictions of what would later become known as Big Bang cosmology. If the universe was expanding now and had been expanding for a finite time in the past, then there must have been a moment of creation, a beginning to space and time itself. This moment would have been characterized by incredible heat and density, conditions unlike anything that exists in the universe today. Belgian physicist and Catholic priest Georges Lemaître was among the first to grasp these implications fully. In 1927, even before Hubble's definitive observations, Lemaître had published a paper proposing what he called the hypothesis of the primeval atom. He envisioned the early universe as a single, super-dense cosmic egg that had undergone a kind of radioactive decay, fragmenting into all the matter and energy we observe today. Lemaitre's primeval atom hypothesis was remarkably prescient, anticipating many features of what we now call the Big Bang theory. He understood that an expanding universe implied a hot, dense beginning, and he recognized that this beginning would have left observable traces in the form of cosmic radiation and the relative abundances of light elements like hydrogen and helium. But Lemaitre's ideas, like Einstein's equations before them, met with significant resistance from the scientific community. The notion of a cosmic beginning seemed to many scientists like a retreat into religious thinking, abandoning the rational, materialistic worldview that had driven scientific progress for centuries. How could science address questions about the origin of existence itself? How could natural processes account for the creation of space and time? The debate over cosmic origins was complicated by technical problems with early versions of Big Bang theory. Using Hubble's initial measurements of the cosmic expansion rate, astronomers calculated that the universe could be only about 2 billion years old. But geological evidence clearly showed that Earth itself was at least twice that age, and stellar evolution models suggested that some stars were even older than Earth. This age problem was one of the main obstacles to accepting Big Bang cosmology throughout the 1930s and 1940s. How could the universe be younger than its own contents? Critics argued that this contradiction proved that the expanding universe interpretation must be wrong, and they continued to search for alternative explanations for Hubble's observations. The age problem wasn't resolved until the 1950s, when astronomers discovered that Hubble had systematically underestimated the distances to galaxies. The Cepheid variable, stars he used as distance indicators, came in two different types, with different intrinsic brightnesses, but this distinction wasn't recognized until decades after Hubble's original work. When the distance scale was corrected, the calculated age of the universe increased to about 10 to 15 billion years, old enough to accommodate all known geological and astronomical ages. But even as technical problems with Big Bang theory were resolved, philosophical resistance remained strong. The idea of a cosmic beginning seemed to violate the principle of sufficient reason, the philosophical doctrine that everything must have an explanation. What could explain the existence of existence itself? What could cause the creation of space and time? These philosophical concerns led some prominent scientists to develop alternative theories that preserved the idea of an eternal universe while still accounting for Hubble's observations. The most influential of these was the steady-state theory, developed by British astronomers Fred Hoyle, Hermann Bondi, and Thomas Gold in the late 1940s. According to the steady-state theory, the universe had always existed in roughly its current form and would continue to exist forever. As space expanded and galaxies moved apart, new matter was continuously created to fill the gaps, maintaining constant density throughout cosmic history. This continuous creation violated the conservation of energy, but proponents argued that the violation was so small, about 1 hydrogen atom per cubic kilometer per billion years, that it would be undetectable by any conceivable experiment. The steady-state theory was philosophically appealing because it avoided the troublesome questions raised by Big Bang cosmology. There was no moment of creation, no first cause, no need to explain how something could come from nothing. The universe had simply always existed, governed by eternal natural laws that required no ultimate explanation. Fred Hoyle, who became the most vocal advocate of the steady-state theory, coined the term Big Bang during a 1949 BBC radio broadcast as a somewhat dismissive description of the competing theory. The name stuck, even though it was somewhat misleading. The Big Bang wasn't really an explosion in the conventional sense, but rather the rapid expansion of space itself. Throughout the 1950s, the debate between Big Bang and steady-state theories dominated cosmology. Both theories could explain Hubble's observations of cosmic expansion, but they made different predictions about other aspects of the universe that could potentially be tested through observation. The Big Bang theory predicted that the early universe had been much hotter and denser than today's cosmos. This should have left observable traces in the form of a cosmic background radiation, the cooled remnant of the intense heat from the universe's beginning. It also predicted specific ratios of light elements like hydrogen, helium, and lithium forged during the first few minutes when the entire universe was hot enough for nuclear fusion. The steady-state theory predicted that these light elements would be produced gradually in stars and supernovae over cosmic time, leading to different abundance ratios. It predicted no cosmic background radiation, since the universe had never been in a uniformly hot, dense state. For more than a decade, neither theory could claim decisive observational support. But by the early 1960s, new observations were beginning to favor the Big Bang model. Radio astronomers discovered quasars, incredibly luminous objects that appeared to exist only at great distances from Earth. If the steady-state theory was correct and the universe had always been roughly the same, distant regions should look identical to nearby ones. The discovery of quasars suggested that the early universe had indeed been different from today's cosmos. But the decisive evidence for Big Bang cosmology came from an unexpected source, an accidental discovery that would revolutionize our understanding of cosmic history and open up entirely new ways of studying the early universe. As the 1960s began, the stage was set for one of the most important discoveries in the history of science. The theoretical framework existed to make testable predictions about the observable consequences of a hot, dense beginning to the universe. The technology existed to detect the faint signals that such a beginning should have left behind. All that remained was for someone to point the right instrument in the right direction and recognize what they were seeing. That moment was about to arrive, and with it would come confirmation that our universe truly did have a beginning, that space, time, matter, and energy all emerged from a primordial state of unimaginable heat and density. The eternal cosmos of ancient philosophy was about to give way to a dynamic, evolving universe with a definite history and an uncertain future. The discovery that would settle the debate between Big Bang and steady-state cosmology was waiting to be made, hidden in the form of a faint whisper of radiation that filled all of space, the afterglow of creation itself. On a crisp spring morning in 1965, two engineers at Bell Telephone Laboratories in New Jersey were about to stumble upon one of the most important discoveries in the history of science. Arnold Penzias and Robert Wilson had no intention of revolutionizing cosmology. They were simply trying to eliminate an annoying source of noise from a sensitive radio antenna, hoping to use it for cutting-edge radio astronomy research. The antenna in question was no ordinary piece of equipment. Originally built for early satellite communications experiments, the 20-foot horn antenna at Bell Labs' Holmdel facility was one of the most sensitive radio receivers ever constructed. Its horn shape was designed to collect radio waves with minimal interference from terrestrial sources, making it perfect for detecting the faint radio signals from distant celestial objects. But Penzias and Wilson were plagued by a persistent problem. No matter where they pointed their antenna, no matter what frequency they tuned to, they detected a constant background hiss that seemed to come from everywhere at once. This cosmic static was interfering with their attempts to study radio emissions from the Milky Way, and they were determined to eliminate it. Their first suspicion fell on a pair of pigeons that had taken up residence inside the antenna horn. Perhaps their droppings were causing electrical problems, creating spurious signals that masked the celestial radio sources they wanted to study. The two researchers embarked on what would later seem like a comically mundane mission. They carefully cleaned the antenna, scraping away every trace of what they politely called white dielectric material from the metal surfaces. When cleaning failed to eliminate the noise, they trapped the offending pigeons and relocated them to a site miles away. But, like homing pigeons, the birds returned to their comfortable roost inside the antenna. Penzias and Wilson repeated this process several times, growing increasingly frustrated as the persistent noise continued to interfere with their observations. They checked their electronic systems methodically, testing every amplifier, cable, and connection. They recalibrated their instruments, adjusted their procedures, and considered every possible source of terrestrial interference they could imagine. Radio signals from New York City, electrical equipment at nearby facilities, even the possibility of nuclear weapons testing creating atmospheric disturbances. Nothing they tried could account for the mysterious signal. What made the noise particularly puzzling was its remarkable uniformity. Unlike terrestrial radio interference, which typically varies in intensity and direction, this signal appeared to come from every direction in the sky with exactly the same strength. It was present day and night, summer and winter, regardless of where they pointed their antenna or what frequency they observed. Meanwhile, just 40 miles away at Princeton University, a team of theoretical physicists led by Robert Dicke was developing plans to search for exactly the kind of signal that Penzias and Wilson were trying to eliminate. Dicke had been thinking deeply about the implications of Big Bang cosmology, and he had realized that if the universe really had begun in a hot, dense state, it should have left behind a detectable afterglow. Dicke's reasoning was based on a detailed understanding of how matter and radiation would have behaved in the early universe. His calculations showed that for the first several 100,000 years after the Big Bang, the cosmos would have been far too hot for atoms to exist. Under such extreme conditions, electrons could not bind to atomic nuclei. They existed instead as a plasma of free particles, creating a universe that was completely opaque to light. Photons, particles of light, and electromagnetic radiation could not travel far in this primordial plasma before colliding with free electrons and being scattered in random directions. The early universe would have been like the interior of a star, where light is constantly absorbed and re-emitted by matter, preventing it from traveling in straight lines over large distances. But as the universe expanded, it also cooled. Eventually, about 80,000 years after the Big Bang, the temperature would have dropped low enough for electrons and protons to combine into neutral hydrogen atoms. This moment, which cosmologists call recombination, would have made the universe transparent to light for the first time in its history. The significance of this transition cannot be overstated. Before recombination, photons were trapped in constant interaction with free electrons, bouncing around randomly without the ability to travel freely through space. After recombination, photons could suddenly travel unimpeded across the cosmos, creating the first clear view of the universe's large-scale structure. These ancient photons from the moment of recombination should still be detectable today, Dicke realized, but they would have been dramatically altered by nearly 14 billion years of cosmic expansion. The same process that stretched space and carried galaxies away from each other would also have stretched the wavelengths of these primordial photons, cooling them from the visible light they once were to much longer, cooler radio waves. Using the laws of thermodynamics and the known rate of cosmic expansion, Dicke and his colleagues calculated that this cosmic background radiation should have a current temperature of just a few degrees above absolute zero. It should appear as thermal radiation with the characteristic spectrum of a black body, an object that absorbs all radiation falling on it and emits radiation according to its temperature alone. Most importantly for observational astronomy, this radiation should be almost perfectly uniform across the entire sky, reflecting the fact that the early universe was incredibly smooth and homogeneous at the moment of recombination. Any observer, anywhere in the universe, should detect this background radiation with the same intensity in every direction. Dicke and his Princeton colleagues were preparing to build their own radio telescope to search for this cosmic microwave background when they learned about the mysterious noise that was frustrating Penzias and Wilson at Bell Labs. Through a mutual acquaintance, word of the Bell Labs team's technical difficulties reached Princeton, and Dicke immediately recognized the significance of what they had found. "Boys, we've been scooped," Dicke reportedly told his colleagues when he learned about the Bell Labs discovery. The annoying background noise that Penzias and Wilson had been trying to eliminate for months was exactly the cosmic microwave background radiation that Big Bang theory predicted. The cosmic microwave background had all the properties that Big Bang cosmology required. It was isotropic, appearing with the same intensity in every direction across the sky. It had the spectrum of perfect blackbody radiation, indicating that it had once been in thermal equilibrium at a much higher temperature. And its current temperature, approximately 2.7 degrees above absolute zero, matched theoretical predictions for radiation that had been cooling for about 14 billion years. When the discovery was announced in 1965, it sent shockwaves through the scientific community. Here was direct observational evidence for the Big Bang theory, proof that the universe had indeed been in a hot, dense state in the distant past. The cosmic microwave background was nothing less than the afterglow of creation itself. a fossil remnant of the moment when the universe first became transparent to light. The discovery effectively ended the long-running debate between Big Bang and steady-state cosmology. The steady-state theory had explicitly predicted that no such background radiation should exist, since the universe had supposedly never been in a uniformly hot, dense state. While Fred Hoyle and other steady-state proponents attempted to develop alternative explanations for the microwave background, these became increasingly contrived and unconvincing as more detailed observations were made. But the cosmic microwave background did more than simply confirm the Big Bang theory. It opened up an entirely new field of precision cosmology. For the first time in history, astronomers had a direct observational window into the early universe, a way to study conditions that existed when the cosmos was less than 400,000 years old. The background radiation was essentially a baby picture of the universe, showing us what the cosmos looked like at the moment when it first became transparent to light. Encoded in the properties of this radiation was information about the density, temperature, and composition of the early universe. By studying the cosmic microwave background in detail, scientists could test theoretical models of cosmic evolution and learn about physical processes operating under conditions that could never be reproduced in terrestrial laboratories. As instruments became more sophisticated over the following decades, astronomers were able to study the cosmic microwave background with ever-increasing precision. What they found confirmed many predictions of Big Bang theory while revealing new puzzles that would drive theoretical developments for generations to come. The radiation was remarkably uniform across the sky, but not perfectly so. Sensitive instruments revealed tiny variations in temperature from one direction to another, typically just a few parts per million. These minute fluctuations were incredibly significant because they represented the seeds from which all cosmic structure would eventually grow. In the smooth, homogeneous early universe revealed by the microwave background, regions that were slightly denser than average would have a slightly stronger gravitational field. Over millions and billions of years, these stronger gravitational fields would attract additional matter, causing the dense regions to become even denser, while sparse regions became even more sparse. This process of gravitational amplification would eventually lead to the formation of the first stars and galaxies, and ultimately to the complex cosmic web of structure we observe today. The tiny temperature fluctuations in the cosmic microwave background were like the DNA of cosmic structure formation, encoding the information that would determine where galaxies, clusters, and superclusters would eventually form. But the cosmic microwave background discovery was just one pillar of evidence supporting Big Bang cosmology. Another crucial confirmation came from studies of the relative abundances of light elements throughout the universe. Big Bang theory made very specific predictions about how much hydrogen, helium, lithium, and other light elements should have been produced in the first few minutes after the universe began. During this brief period, when the entire cosmos was hotter than the core of the Sun, nuclear fusion reactions would have converted some primordial hydrogen into heavier elements. The amount of each element produced would depend on the exact conditions during these first minutes, the temperature, density, and rate of expansion of the universe. By calculating these conditions based on our understanding of nuclear physics and cosmology, theorists could predict the ratios of light elements that should be observed in the universe today. These predictions were remarkably successful. Observations showed that about 75% of normal matter in the universe is hydrogen, with roughly 25% helium and traces of lithium, exactly matching the ratios predicted by Big Bang nuclear synthesis theory. This agreement was particularly impressive because it involved nuclear physics processes operating under conditions of temperature and density far more extreme than anything achievable in laboratory experiments. The success of Big Bang nuclear synthesis provided independent confirmation of the hot, dense early universe implied by the cosmic microwave background discovery. It also established important constraints on the properties of the early cosmos, including the total amount of normal matter and the rate of cosmic expansion during the first few minutes. But perhaps most significantly, the combination of cosmic microwave background observations and Big Bang nucleosynthesis calculations revealed that normal matter, The protons, neutrons, and electrons that make up stars, planets, and living beings constitutes only a small fraction of the universe's total contents. When astronomers added up all the normal matter they could observe or infer from Big Bang nuclear synthesis, they found that it amounted to less than 5% of the total energy density required to explain cosmic expansion and structure formation. The remaining 95% of the universe appeared to consist of unknown forms of matter and energy that interact only weakly, if at all, with ordinary matter and light. This revelation led to one of the most profound mysteries in modern science. If most of the universe consists of dark matter and dark energy that we cannot directly observe, what are these mysterious components? How do they affect cosmic evolution? And what does their existence tell us about the fundamental nature of reality? The discovery of cosmic microwave background radiation had solved one great mystery, confirming that the universe began in a hot, dense state, but it had also revealed new puzzles that would challenge scientists for decades to come. The Big Bang theory was established as the best explanation for cosmic origins, but many fundamental questions remained unanswered. Why was the early universe so remarkably uniform and smooth? The cosmic microwave background showed that regions now separated by billions of light years had nearly identical temperatures, despite having no apparent way to communicate and equilibrate with each other. This horizon problem suggested that some new physics was needed to explain the universe's initial conditions. Why was the geometry of space so close to perfectly flat? Observations indicated that the universe's expansion rate was balanced almost exactly with its matter content, producing a geometry where parallel lines never converge and the angles of triangles add up to precisely 100 in dead. But achieving this flatness required incredible fine-tuning of initial conditions. Any significant deviation would have led to a universe that either collapsed quickly or expanded so rapidly that no structure could form. And where were the exotic particles that theories of fundamental physics predicted should have been produced in the extreme conditions of the early universe? Grand unified theories suggested that magnetic monopoles, hypothetical particles carrying isolated magnetic charge, should have been created in enormous quantities during the first fraction of a second. Yet, despite extensive searches, no magnetic monopoles had ever been detected. These puzzles suggested that the Big Bang theory, successful as it was still incomplete. Some new theoretical framework was needed to explain not just how the universe evolved from its earliest observable moments, but why it began with the particular properties that allowed stars, galaxies, and ultimately life to form. The answer to these puzzles would come from an unexpected direction, from theoretical physicists studying the behavior of quantum fields in the extreme conditions of the very early universe. Their work would lead to one of the most revolutionary ideas in modern cosmology, the theory of cosmic inflation. But inflation theory would do more than solve the technical problems of Big Bang cosmology. It would suggest that our entire observable universe might be just one small bubble in an infinite multiverse, raising profound questions about the nature of existence and our place within it. The story of how Big Bang theory evolved into our modern understanding of cosmic origins is a testament to the power of scientific methodology. Theoretical predictions, observational discoveries, and technological advances combined to reveal a universe far stranger and more wonderful than our ancestors could have imagined. From Hubble's discovery of cosmic expansion to Penzias and Wilson's accidental detection of the cosmic microwave background, each breakthrough built upon previous knowledge while opening new frontiers of investigation. The Big Bang theory emerged not as a single revolutionary insight, but as the culmination of decades of careful observation, mathematical analysis, and theoretical development. Yet even as the Big Bang became established as the standard model of cosmology, scientists recognized that it raised as many questions as it answered. The theory successfully explained how the universe evolved from a hot, dense beginning into the complex cosmos we observe today, but it said nothing about what caused that beginning or what, if anything, might have existed before it. These deeper questions about ultimate origins would require new theoretical frameworks that pushed the boundaries of physics itself. Scientists would need to explore the interface between quantum mechanics and gravity, investigate the behavior of matter and energy under conditions more extreme than those found anywhere in the observable universe, and grapple with concepts that challenged basic assumptions about space, time, and causality. The journey from the discovery of cosmic expansion to our modern understanding of the Big Bang had taken half a century and involved some of the most brilliant minds in science. But this was only the beginning of humanity's quest to understand cosmic origins. The next phase of this journey would venture into even more exotic territory, where the familiar concepts of physics give way to theories so strange they seem to belong more to science fiction than to science. The cosmic microwave background had provided a window into the early universe, but it could only reveal conditions that existed 80,000 years after the initial moment of creation. What happened during those first crucial moments remained hidden behind an impenetrable veil. To peer behind that veil and understand the ultimate origins of space, time, matter, and energy would require new ideas that stretched scientific imagination to its limits. The stage was set for the next great revolution in cosmology, one that would suggest our universe began not with a singular Big Bang, but with a period of exponential expansion that created not just our cosmos, but potentially an infinite number of parallel universes. The story of cosmic origins was about to become even stranger and more wonderful than anyone had dared to imagine. On a cold December evening in 1979, a young physicist at Stanford University was about to have an insight that would revolutionize our understanding of cosmic origins. Alan Guth was working late in his office, struggling with equations that described the behavior of quantum fields in the extreme conditions of the early universe. He was investigating phase transitions, dramatic changes in the properties of matter that occur when temperature and pressure cross certain critical thresholds. Guth wasn't originally a cosmologist. His background was in particle physics, studying the fundamental forces and particles that govern matter at the smallest scales. But like many theoretical physicists of his generation, he had become fascinated by grand unified theories, ambitious attempts to show that the electromagnetic, weak nuclear, and strong nuclear forces were actually different aspects of a single, more fundamental force. These grand unified theories made remarkable predictions about the early universe. They suggested that in the first fraction of a second after the Big Bang, when temperatures were billions of times hotter than the core of the Sun, the fundamental forces of nature would have been unified into a single superforce. As the universe expanded and cooled, this unified force would have undergone a series of phase transitions, breaking apart into the distinct forces we observe today. Phase transitions are common in everyday experience. Water undergoes a phase transition when it freezes into ice or boils into steam. The underlying molecules remain the same, but their organization and properties change dramatically. Similarly, the unified force of the early universe would have undergone phase transitions as cosmic temperatures dropped below critical values. But Guth realized that these cosmological phase transitions might be very different from familiar examples like freezing water. Under certain conditions, the universe might get temporarily stuck in a metastable state, a condition that's temporarily stable but not the lowest possible energy state. This would be like water that has been cooled below its freezing point but hasn't yet formed ice crystals, remaining liquid despite being in a thermodynamically unstable condition. If the early universe became trapped in such a metastable state, the consequences would be extraordinary. The energy density associated with this false vacuum would act like Einstein's cosmological constant, a form of energy that causes space itself to expand exponentially rather than the gradually decelerating expansion observed in the universe today. As Guth worked through the mathematics of this scenario, he began to realize that a brief period of exponential expansion in the early universe could solve several major problems that plagued Big Bang cosmology. The horizon problem, the flatness problem, and the monopole problem. Puzzles that had bothered cosmologists for years might all have elegant solutions if the universe had undergone a period of exponential expansion in its earliest moments. The horizon problem arose from the remarkable uniformity of the cosmic microwave background radiation. This ancient light showed that regions of the early universe, now separated by billions of light years, had nearly identical temperatures. But according to standard Big Bang theory, these regions should never have been in causal contact. Light hadn't had enough time since the Big Bang to travel between them and establish thermal equilibrium. Exponential expansion could solve this puzzle. If a tiny region of space, small enough to be in thermal equilibrium, was suddenly stretched by an enormous factor, it could encompass what we now observe as the entire visible universe. Regions that appear disconnected today would actually have been in close contact before the period of rapid expansion began. The flatness problem involved the geometry of space itself. Observations showed that the universe appeared to be geometrically flat. Parallel lines never converge, and the angles of triangles add up to exactly 100 degrees. But achieving this flatness required an incredibly precise balance between the expansion rate and the matter density of the universe. Any significant deviation from this precise balance would have led to a universe that either collapsed quickly or expanded so rapidly that no structure could form. Exponential expansion could solve this problem too. Just as inflating a balloon makes its surface appear increasingly flat to small observers on its surface, exponential expansion of space would drive the geometry toward perfect flatness regardless of what it had been initially. The universe could have started with any curvature, but a period of rapid expansion would stretch space so much that it would appear flat on observable scales. The monopole problem arose from predictions of grand unified theories. These theories suggested that the extreme conditions of the early universe should have produced enormous numbers of magnetic monopoles, hypothetical particles that carry isolated magnetic charge. Such particles would be incredibly massive and completely stable, so they should still exist in large numbers today. But despite extensive searches, no magnetic monopoles had ever been detected. Exponential expansion could solve this problem as well. If magnetic monopoles were produced before the period of rapid expansion, they would be diluted to such low densities that we would never expect to encounter one in the observable universe. The expansion would spread the monopoles so far apart that they would become essentially undetectable. As these realizations dawned on him, Guth became increasingly excited. Here was a single mechanism that could solve multiple problems with Big Bang cosmology while making new, testable predictions about the universe's structure. He called this period of exponential expansion inflation, and he began to work out its detailed implications. According to Guth's calculations, inflation would have lasted for an incredibly brief time, perhaps from 10⁻⁻36 to 10⁻32 seconds after the Big Bang. But during this tiny interval, the universe would have grown by an enormous factor. The minimum amount of expansion required to solve the horizon and flatness problems was about 10 Nelson 26, a factor so large that it defies easy comprehension. To get a sense of this scale, imagine a region initially smaller than a proton, expanding to the size of a grapefruit in less time than it takes light to cross the nucleus of an atom. This is the kind of exponential growth that inflation theory requires. Yet despite this seemingly impossible rate of expansion, inflation doesn't violate Einstein's prohibition on faster-than-light travel because space itself is expanding rather than matter moving through space. Guth announced his inflation theory at a seminar at the Stanford Linear Accelerator Center in January 1980. The response was immediate and enthusiastic. Here was an elegant theoretical framework that solved multiple observational puzzles while providing a physical mechanism for the initial conditions required by Big Bang cosmology. But Guth's original inflation model had a serious technical problem that became apparent as he and other physicists worked out its detailed implications. The issue was what became known as the graceful exit problem. Once inflation began, it seemed impossible to stop it cleanly and transition to the hot, dense state required for standard Big Bang evolution. The problem arose from the very mechanism that drove inflation in the first place. The false vacuum state that caused exponential expansion was metastable. It would eventually decay to a lower energy state, but this decay process proved difficult to control in Guth's original model. Instead of ending smoothly and uniformly throughout space, inflation tended to end in scattered bubbles that would be separated by regions still undergoing exponential expansion. This wouldn't produce the smooth, homogeneous universe revealed by the cosmic microwave background. Instead, it would create a cosmos filled with enormous bubbles of normal space separated by vast regions of inflating false vacuum. Observers inside one bubble wouldn't be able to see other bubbles, and the universe would be far more inhomogeneous than observations indicated. For several years, this graceful exit problem seemed like a fatal flaw in inflation theory. Many physicists began to lose interest in the idea, thinking it was an elegant solution that unfortunately didn't work in practice. But Guth and other theorists continued to work on the problem, convinced that the basic insight of inflation was correct, even if the details needed to be refined. The breakthrough came from several directions simultaneously. In 1982, Andrei Lind at Moscow's Lebedev Physical Institute proposed a modified version called new inflation that avoided the graceful exit problem. Around the same time, Andreas Albrecht and Paul Steinhardt at the University of Pennsylvania developed a similar solution. Their slow-roll inflation models showed how inflation could begin and end smoothly, leaving behind a hot, dense state that would evolve according to standard Big Bang theory. The key insight was that inflation didn't require the universe to be trapped in a false vacuum state. Instead, it could be driven by a quantum field, the inflaton, that rolled slowly down a potential energy curve. Like a ball rolling down a very gentle slope, the inflaton field would change gradually, causing the energy density of space to decrease slowly during inflation. This slow evolution allowed inflation to end gracefully when the inflaton field reached the bottom of its potential energy curve. At that point, the field would oscillate around its minimum value, and these oscillations would decay into the ordinary particles of matter and radiation that fill the universe today. This reheating process would create the hot, dense conditions required for Big Bang nucleosynthesis and the eventual formation of the cosmic microwave background. The success of new inflation models reinvigorated interest in inflationary cosmology. Not only did these models solve the original problems that had motivated Guth's work, but they also made new predictions that could be tested through observations of the cosmic microwave background and large-scale structure of the universe. One of the most important predictions involved the tiny fluctuations in the cosmic microwave background that had been detected by increasingly sensitive instruments. According to inflation theory, these fluctuations arose from quantum mechanical uncertainty in the inflaton field during the period of exponential expansion. In the quantum world, even empty space is filled with random fluctuations that briefly create particle-antiparticle pairs before they annihilate each other. During inflation, these quantum fluctuations in the inflaton field would be stretched to macroscopic scales by the exponential expansion of space. Regions where the field fluctuated to slightly higher values would end up with slightly higher energy density, while regions with lower values would have lower density. These density fluctuations, initially tiny and quantum mechanical in origin, would eventually grow under the influence of gravity to become the galaxies, clusters, and large-scale structures we observe today. The pattern of temperature fluctuations in the cosmic microwave background provides a fossilized record of these primordial quantum fluctuations, stretched to cosmic scales by inflation. This connection between quantum mechanics and cosmology was one of the most profound insights of inflation theory. It suggested that the large-scale structure of the universe, the distribution of galaxies across billions of light years, might have originated from quantum uncertainty on subatomic scales. The universe's greatest structures would thus have quantum mechanical origins, representing a remarkable unification of the very large and the very small. But inflation theory led to an even more radical possibility that would fundamentally change how cosmologists think about the universe and our place within it. As physicists developed more sophisticated models of inflation, they realized that the process might not have a definite beginning or end. Instead, inflation might be an eternal process that continues forever in some regions of space while ending in others. This possibility arises from the quantum nature of the inflaton field. Just as the quantum fluctuations during inflation create density variations that lead to structure formation, they also create variations in the inflaton field itself. In some regions, these fluctuations cause the field to decay and inflation to end, creating bubble universes like our own. But in other regions, the fluctuations cause inflation to continue, maintaining the exponential expansion. The mathematics of this process are both beautiful and terrifying in their implications. In regions where inflation continues, space expands exponentially, doubling in size every 10 to 35 seconds or so. but quantum fluctuations constantly create new bubbles where inflation ends and normal cosmic evolution begins. Each bubble expands rapidly once inflation ends within it, but can never grow fast enough to catch up with the exponentially expanding background. This leads to the concept of eternal inflation, the idea that once inflation starts anywhere in space, it continues forever, constantly creating new bubble universes while maintaining exponential expansion in the regions between bubbles. Our entire observable universe would be just one such bubble, one small region where inflation ended and normal physics took over. The implications of eternal inflation are staggering. If this picture is correct, then our Big Bang was not unique. It was just one bubble formation among an infinite number of such events occurring throughout an eternally inflating multiverse. Each bubble universe would have its own Big Bang, its own evolution, and potentially its own physical laws. The number of these bubble universes would be literally infinite, and they would exhibit every possible variation in physical properties. Some might have stronger gravity, causing stars to burn out quickly and preventing the formation of long-lived planetary systems. Others might have weaker electromagnetic forces, making it impossible for atoms to form stable chemical bonds. Still others might have completely different numbers of spatial dimensions, different types of particles, or different mathematical structures governing their physics. But the multiverse would also contain bubbles almost identical to our own, differing only in minor details. In some bubbles, you chose a different career path. In others, the dinosaurs never went extinct and evolved into intelligent civilizations. In still others, the fundamental constants are shifted by tiny amounts, leading to subtly different outcomes in cosmic evolution. This infinite ensemble of universes provides a potential explanation for one of the most puzzling aspects of our cosmos, the apparent fine-tuning of physical constants for the existence of complexity and life. The strength of gravity, the mass of the electron, the rate of cosmic expansion, and dozens of other parameters seem to be precisely adjusted to allow stars to shine, planets to form, and chemistry to work in ways that support complex structures. If there's only one universe, this fine-tuning might seem to require either incredible luck or intelligent design. But if there are infinitely many universes with different values of these parameters, then we naturally find ourselves in one where the parameters are compatible with our existence. We couldn't exist in universes where the constants are incompatible with complexity and life, so we necessarily observe a universe where they're favorable. This anthropic reasoning has become increasingly important in cosmology, providing a framework for understanding apparent cosmic coincidences without invoking supernatural intervention. But it's also controversial because it seems to abandon the traditional goal of physics, finding fundamental explanations for why things are the way they are. If the constants of nature are just environmental accidents that vary randomly from one universe to another, then perhaps there's no deeper reason why they have the values we observe. We see what we see, not because of fundamental principles, but because we happen to live in a universe where these particular values allow observers like us to exist. This represents a profound shift in how we think about scientific explanation. Rather than seeking unique, mathematically determined values for the fundamental constants, we might need to accept that they're contingent features of our local cosmic environment, no more fundamental than the temperature on Earth or the chemical composition of our atmosphere. The multiverse concept raises equally profound questions about the nature of existence and identity. If there are infinite copies of you living slightly different lives in parallel universes, what makes your particular existence special or meaningful? If every possible universe exists somewhere in the multiverse, does the concept of natural law lose its significance? How can we test scientific theories about regions of space-time that are, by definition, unobservable? These questions push us toward the boundaries of what can be considered science in the traditional sense. The multiverse, if it exists, is fundamentally unobservable from our perspective. We can never travel to other bubble universes or communicate with their inhabitants. Any theory that depends on the existence of unobservable entities faces serious challenges to its scientific status. But perhaps the multiverse isn't entirely beyond observational reach. While we can't observe other bubble universes directly, we might be able to detect indirect evidence of their existence. If our bubble universe collided with another bubble in the distant past, it should have left distinctive signatures in the cosmic microwave background, unusual patterns of temperature or polarization that we could detect with sufficiently sensitive instruments. Several research groups have claimed to identify such anomalies in cosmic microwave background data. The European Space Agency's Planck satellite detected what appeared to be a significant cold spot, a region where the temperature is notably lower than the surrounding area. Some researchers initially suggested this could be evidence of a collision with another bubble universe, though subsequent analysis indicated it was more likely due to chance or other astrophysical effects. The search for multiverse signatures has become an active area of research, with cosmologists developing increasingly sophisticated techniques for analyzing the cosmic microwave background. Future space missions might be sensitive enough to detect the subtle signatures that bubble collisions would leave in the ancient radiation. But even if we find evidence for the multiverse, this would only deepen the mystery of cosmic origins. Where did the eternally inflating background come from in the first place? What started the process of eternal inflation? What determined the physical laws that govern the multiverse as a whole? These questions push us beyond the framework of inflation theory into even more speculative territory. To address them, we need to venture into the strange world of quantum mechanics, where the normal rules of causation and existence don't apply in familiar ways. We need to explore the possibility that our entire universe might have emerged from quantum fluctuations in a realm where space and time themselves might not exist. The journey from Alan Gut's late-night insight to our modern understanding of eternal inflation and the multiverse represents one of the most remarkable developments in the history of science. Starting with the modest goal of solving technical problems in Big Bang cosmology, inflation theory has led us to contemplate the existence of infinitely many parallel universes, each with its own Big Bang and its own evolutionary history. This theoretical journey illustrates both the power and the challenge of modern physics. Mathematical reasoning and physical intuition can lead us to conclusions that seem almost too strange to believe, yet these conclusions emerge naturally from our best understanding of quantum mechanics and general relativity. The universe revealed by inflation theory is far more vast, complex, and mysterious than anything our ancestors could have imagined. But inflation theory also demonstrates the provisional nature of scientific knowledge. Each answer leads to new questions, each solution reveals new puzzles, each horizon crossed exposes further mysteries beyond. The inflationary universe may solve the problems of Big Bang cosmology, but it raises profound new questions about the nature of existence, the meaning of physical law, and our place in a potentially infinite cosmos. As we stand at the beginning of the 21st century with increasingly powerful instruments for studying the cosmic microwave background and mapping the large-scale structure of the universe, we may be on the verge of answering some of these questions. Future observations might provide definitive evidence for inflation, detect signatures of the multiverse, or reveal new phenomena that require entirely new theoretical frameworks. But whatever we discover, the legacy of inflation theory will endure. It has shown us that the universe is stranger and more wonderful than we ever dared imagine, and it has opened our minds to possibilities that stretch the boundaries of human comprehension. In trying to understand what came before the Big Bang, we have discovered that the Big Bang itself might be just the beginning of an infinite story of cosmic creation and evolution. The inflationary universe has taken us from the comfortable certainties of a single cosmos with a definite beginning to the mind-bending possibility of infinite parallel realities. But this is still not the end of our journey into the deepest mysteries of existence. To understand what might have triggered inflation itself, we need to venture even further into the quantum realm, where the boundary between something and nothing becomes blurred and where the very concepts of space, time, and causality might break down entirely. The next phase of our exploration will take us to the very foundations of reality itself, to the question of how something can emerge from nothing and whether the universe could have created itself through pure quantum processes. We're about to discover that the rabbit hole of cosmic origins goes deeper than anyone ever imagined. In the basement of a physics laboratory at Columbia University in 1948, a young Dutch physicist named Hendrik Casimir was pondering one of the strangest predictions ever made by quantum mechanics. According to the theory, empty space, What we call the vacuum was not actually empty at all. Instead, it was filled with an invisible sea of energy that constantly bubbled with the creation and destruction of virtual particles. This wasn't merely a theoretical curiosity. Casimir realized that if the quantum vacuum really contained energy, it should be possible to detect this energy through its effects on ordinary matter. He proposed a remarkably simple experiment. Take two uncharged metal plates, place them very close together in a perfect vacuum, and measure whether they experienced any force. Classical physics predicted that nothing should happen. Uncharged plates in empty space should remain motionless, unaffected by any forces. But quantum mechanics suggested something very different. The virtual particles that constantly pop in and out of existence in the vacuum should create a measurable pressure difference between the plates and the surrounding space. The reasoning behind this prediction reveals just how strange quantum mechanics really is. According to quantum field theory, every point in space is filled with quantum fields, invisible entities that can create particles when they're excited, like waves on an ocean creating whitecaps when disturbed by wind. Even when no real particles are present, these fields are never completely still. They fluctuate randomly, creating virtual particle pairs that exist for infinitesimally brief moments before annihilating each other and disappearing back into the vacuum. These virtual particles aren't just mathematical abstractions, they have real, measurable effects. Between Casimir's closely spaced plates, only virtual particles with wavelengths smaller than the gap can exist. But in the space outside the plates, virtual particles of all wavelengths can fluctuate freely. This creates an imbalance. There's more vacuum energy outside the plates than between them, resulting in a net force that pushes the plates together. When Casimir's prediction was finally tested experimentally in 1958, the results confirmed quantum field theory with remarkable precision. The Casimir effect demonstrated that empty space is not empty, it's a seething sea of quantum activity that can exert measurable forces on ordinary matter. This discovery would have profound implications for our understanding of cosmic origins. If virtual particles can create forces strong enough to move metal plates in a laboratory, what might they be capable of on cosmic scales? Could the quantum vacuum have played a role in the creation of the universe itself? These questions would drive theoretical physicists to explore increasingly radical possibilities about the nature of existence and the origin of everything. The quantum mechanical picture of reality is profoundly different from our everyday experience. In the familiar world of classical physics, objects have definite positions, velocities, and other properties. Cause follows effect in predictable sequences. Something cannot come from nothing without violating fundamental conservation laws. But quantum mechanics reveals that reality operates according to very different rules at the smallest scales. Particles can exist in multiple states simultaneously, a phenomenon called superposition. They can tunnel through barriers they don't have enough energy to cross. They can be created from pure energy and annihilated back into energy with perfect efficiency. Most remarkably, they can appear spontaneously from the vacuum, borrowing energy from empty space itself. This last property, the ability of particles to emerge from nothing, is governed by Heisenberg's uncertainty principle, one of the most fundamental concepts in quantum mechanics. Werner Heisenberg discovered that certain pairs of properties, such as energy and time, cannot be measured simultaneously with perfect precision. The more accurately you know one, the less accurately you can know the other. This uncertainty isn't due to limitations in our measuring instruments, it's a fundamental feature of reality itself. The universe seems to operate on a kind of cosmic credit system, where energy can be borrowed from the vacuum as long as it's paid back quickly enough. The amount of energy that can be borrowed and the time for which it can be borrowed are related by Heisenberg's uncertainty principle. The more energy you borrow, the faster you have to pay it back. Virtual particles represent the universe taking advantage of this quantum credit system. Electron-positron pairs pop into existence, exist for a brief moment, allowed by the uncertainty principle, then annihilate each other and disappear back into the vacuum. The entire process happens so quickly that it doesn't violate conservation of energy on average, but it creates measurable effects like the Casimir force. This quantum picture of the vacuum overturns centuries of philosophical thinking about the nature of nothingness. Aristotle had argued that nature abhors a vacuum, believing that truly empty space couldn't exist. Medieval philosophers debated whether God could create a space with nothing in it. René Descartes assumed that space itself was a kind of substance, while Isaac Newton treated it as an empty container for matter and energy. But quantum mechanics revealed that the philosophical concept of absolute nothingness, the complete absence of everything, might be physically impossible. Even when all matter and radiation are removed from a region of space, quantum fields remain, and these fields are never completely inactive. The vacuum state of quantum field theory is not empty, but represents the lowest possible energy state of the fields. This insight led some physicists to wonder whether the entire universe might be understood as a quantum phenomenon. If virtual particles can emerge from the vacuum on microscopic scales, could entire universes emerge from quantum fluctuations on cosmic scales? This seemingly outrageous idea was first seriously proposed by physicist Edward Tryon in 1973. Tryon was attending a lecture on cosmology at Columbia University when the speaker mentioned the puzzle of why the universe exists at all. Almost without thinking, Tryon raised his hand and said, "Maybe the universe is a vacuum fluctuation." The audience laughed, assuming he was making a joke. But Tryon was serious, and over the following months, he developed this offhand comment into a detailed scientific proposal. Tryon's insight was based on a remarkable property of the universe that few people had previously noticed. When you add up all the energy in the cosmos, the mass energy of every star, planet, and particle, plus the kinetic energy of their motion through space, you get an enormous positive number. But when you also account for gravitational potential energy, which is negative because it takes energy to pull masses apart against gravity, the total might actually be zero. This possibility had been recognized by theoretical physicists, but not widely discussed. If the universe's total energy content really is zero, then no energy would be required to create it from the quantum vacuum. The universe would be the ultimate free lunch, a cosmic something for nothing that doesn't violate any conservation laws because nothing is actually being created in net terms. Tryon's proposal was revolutionary because it suggested that the universe's existence might not require any special explanation beyond the normal operation of quantum mechanics. Just as virtual particles spontaneously appear and disappear in the laboratory, entire universes might spontaneously appear and disappear on much larger scales. Our cosmos would be like a massive virtual particle that has existed for 14 billion years but will eventually decay back into the vacuum from which it came. The idea that the universe could create itself through quantum processes was so radical that most physicists initially dismissed it. How could something as vast and complex as the cosmos emerge from the microscopic quantum fluctuations described by particle physics? Even if the total energy was zero, wouldn't the creation of space and time itself require some kind of external cause? But as inflation theory developed in the 1980s, Tryon's ideas began to seem less outrageous. Inflation showed how tiny quantum fluctuations could be stretched to cosmic scales, creating the seeds of all cosmic structure. If quantum processes could generate the matter and energy content of the universe through inflation, why couldn't they also generate the universe itself through vacuum fluctuation? The connection between quantum mechanics and cosmology became even stronger as physicists developed more sophisticated theories of the early universe. Quantum field theory in curved space-time revealed that the boundary between real and virtual particles becomes blurred in strong gravitational fields. Black holes, for example, can convert virtual particles into real ones through a process that causes the black holes to slowly evaporate. Stephen Hawking's discovery of black hole radiation demonstrated that the quantum vacuum behaves very differently in the presence of intense gravity. Virtual particles that would normally annihilate each other can be separated by the extreme curvature of space-time near a black hole's event horizon. One particle falls into the black hole while the other escapes to infinity, becoming a real particle in the process. If black holes can create real particles from virtual ones, might the intense gravitational fields of the early universe have played a similar role in cosmic creation? The Big Bang itself represents conditions of extreme space-time curvature, where the normal distinction between real and virtual particles might break down entirely. This realization led physicists to explore even more exotic scenarios for cosmic origins. Perhaps the universe began not as a singular point of infinite density, but as a quantum fluctuation in some higher dimensional space. Perhaps our familiar three-dimensional space and one-dimensional time are emergent properties of more fundamental quantum processes operating in realms we can't directly observe. The implications of quantum cosmology extend far beyond the technical details of particle physics and general relativity. If the universe really can create itself through quantum processes, then the age-old philosophical question, why is there something rather than nothing, might have a surprisingly simple answer, because nothing, in the quantum mechanical sense, is actually something, a seething sea of virtual particles and quantum fields with the potential to create universes. But this raises deeper questions about the nature of nothingness itself. What exactly do we mean by nothing? The quantum vacuum is clearly not nothing in the absolute philosophical sense. It has structure, energy, and the capacity to create particles. It exists within a framework of space, time, and physical laws. Where did this framework come from? Some physicists have proposed that space and time themselves might be emergent properties of more fundamental quantum processes. In this view, what we think of as the fabric of space-time might actually be a kind of quantum condensate, a collective state of more basic quantum entities that we can't observe directly. This idea finds support in certain approaches to quantum gravity, where space and time are not fundamental but arise from the entanglement patterns of quantum information. Just as temperature and pressure emerge from the microscopic motion of molecules, space-time might emerge from the microscopic dynamics of quantum bits of information. If this picture is correct, then asking what came before the Big Bang might be meaningless. Time itself would be an emergent property that only makes sense within the context of our particular universe. The creation of the universe wouldn't be an event that occurred at a specific moment in time. It would be the process by which time itself came into existence. This perspective suggests that the ultimate ground of reality might be neither matter nor energy nor even space-time, but information, patterns of correlation and entanglement that exist in some timeless, spaceless realm. The physical world we observe would be one possible realization of these abstract informational patterns, like a particular solution to a vast quantum equation. But even this informational view of reality faces the fundamental question of existence. Why do informational patterns exist rather than not exist? What gives abstract quantum states the power to manifest as concrete physical reality? We seem to face an infinite regress where every level of explanation points to deeper mysteries beneath. Perhaps this infinite regress is itself a clue to the nature of ultimate reality. If every explanation requires a deeper explanation, perhaps reality consists of infinite layers of structure and complexity, with no ultimate foundation or final answer. This would be a universe where every discovered truth reveals new questions, where every solved mystery opens doors to greater mysteries beyond. The quantum mechanical picture of cosmic origins represents a profound shift from classical thinking about causation and existence. Rather than looking for a first cause or prime mover, quantum cosmology suggests that existence might be self-generating, arising naturally from the inherent creativity of quantum processes operating according to mathematical principles. This doesn't eliminate the mystery of existence, it transforms it. Instead of asking what caused the universe to exist, we can ask why quantum mechanics takes the particular mathematical form that allows universe creation. Instead of seeking the origin of matter and energy, we can explore the origin of the quantum fields and principles that govern their behavior. These deeper questions push us toward the boundaries of physics and into the realm of mathematics itself. If quantum mechanics is fundamentally mathematical in nature, then understanding cosmic origins might require understanding why mathematics itself exists and why it takes the forms that govern physical reality. The journey from Casimir's simple experiment with metal plates to speculations about quantum universe creation illustrates how scientific investigation can lead us to conclusions that challenge our most basic assumptions about reality. What began as a test of quantum field theory predictions has evolved into a radical new perspective on the nature of existence itself. The quantum vacuum, revealed through experiments like Casimir's, shows us that empty space is not empty, but filled with creative potential. Virtual particles demonstrate that the boundary between existence and non-existence is not sharp, but fuzzy, governed by probabilistic quantum rules rather than deterministic classical laws. The uncertainty principle suggests that reality operates on borrowed time and energy, maintaining its existence through a delicate balance of quantum credit and debt. If these quantum processes can create particles from nothing in laboratory experiments, and if they can create cosmic structure through inflation, then perhaps they can create entire universes through vacuum fluctuations. Our cosmos might be just one bubble of inflated quantum foam in an infinite sea of creative potential, where universes are constantly being born from pure possibility. But quantum mechanics also reveals the limits of human intuition when confronting the deepest aspects of reality. The quantum world operates according to rules that seem to violate common sense, where effects can precede causes, where particles can exist in multiple states simultaneously, and where the act of observation changes the reality being observed. These strange features of quantum mechanics become even more mysterious when applied to cosmology. If the universe began as a quantum fluctuation, what observed it and caused its wave function to collapse into definite existence? If quantum processes created space and time, how can we use concepts like before and after to describe this creation? If reality is fundamentally probabilistic, what determines which possibility becomes actual? These questions push beyond the boundaries of current scientific knowledge into realms where physics, philosophy, and even theology converge. The quantum origin of the universe might explain how something can come from nothing, but it also raises profound new questions about the nature of physical law, mathematical truth, and conscious observation. As we stand at the beginning of the 21st century, with increasingly powerful tools for probing the quantum nature of reality, we may be approaching answers to some of these questions. Experiments in quantum foundations are testing the limits of quantum mechanics and exploring its connections to gravity and space-time. Cosmological observations are providing new data about the early universe and its quantum origins. But whatever answers we find, the quantum perspective on cosmic origins has already transformed our understanding of existence itself. It has shown us that the universe is stranger and more creative than our classical intuition suggested, where something can indeed emerge from nothing through the natural operation of quantum processes. The implications extend far beyond cosmology into questions about consciousness, free will, and the nature of reality itself. If quantum mechanics governs the creation of universes, it might also govern the emergence of minds capable of understanding their own quantum origins. We might be quantum beings living in a quantum cosmos, products of the same creative processes that brought space, time, matter, and energy into existence. Yet even as quantum mechanics provides potential answers to age-old questions about cosmic origins, it also reveals new depths of mystery. The quantum vacuum that can create universes is itself a complex entity with structure and properties that require explanation. The mathematical laws that govern quantum behavior exist in some sense independently of the physical reality they describe. This brings us to one of the most radical possibilities in modern physics and philosophy, the idea that mathematics itself might be the fundamental reality from which everything else emerges. If the universe is quantum mechanical in nature, and if quantum mechanics is purely mathematical, then perhaps physical reality is nothing more than the playing out of abstract mathematical relationships. This mathematical universe hypothesis would represent the ultimate unification of physics and mathematics, suggesting that the boundary between abstract mathematical truth and concrete physical reality is itself an illusion. Numbers, equations, and geometric relationships wouldn't just describe the universe. They would be the universe, existing as pure mathematical entities in some timeless realm of abstract truth. Such ideas push us to the very limits of human comprehension, where the familiar categories of thought begin to break down and dissolve. But they also represent the logical extension of our scientific journey from classical physics through relativity and quantum mechanics toward an ever deeper understanding of the nature of existence itself. The quantum origin of the universe remains one of the most speculative and controversial topics in modern science. But even if these ideas prove incorrect, they have already expanded our conception of what is possible and challenged us to think more deeply about the fundamental nature of reality. They remind us that the universe is under no obligation to conform to our intuitions and expectations, and that the truth about cosmic origins might be stranger and more wonderful than anything we can currently imagine. As we prepare to venture even deeper into the mathematical foundations of reality itself, we carry with us the quantum insight that existence might be self-creating, emerging naturally from the inherent creativity of mathematical and physical law. The question is no longer just what came before the Big Bang, but what lies behind the quantum processes that might have created everything from nothing, and what gives mathematical truth the power to manifest as physical reality. The rabbit hole of cosmic origins continues to beckon us deeper toward mysteries that challenge not just our understanding of the universe, but our understanding of understanding itself. In 1960, physicist Eugene Wigner published a paper with a peculiar title that would haunt scientists and philosophers for decades to come: The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Wigner's central puzzle was deceptively simple, yet profoundly mysterious. Why does mathematics work so well in describing the physical world? Consider the strangeness of this situation. Mathematics is a purely abstract discipline dealing with numbers, equations, and geometric relationships that exist only in the realm of thought. Mathematicians work with concepts like infinite dimensional spaces, imaginary numbers, and non-Euclidean geometries that have no obvious connection to physical reality. Yet when physicists apply these abstract mathematical tools to understanding the universe, they work with almost miraculous precision. Einstein's equations of general relativity, written in the abstract language of tensor calculus and differential geometry, predict the behavior of black holes, the expansion of the cosmos, and the bending of light by gravity. Schrödinger's equation, formulated using complex numbers and probability amplitudes that have no direct physical meaning, successfully describes the behavior of electrons in atoms and the operation of quantum computers. Maxwell's equations, expressed in terms of abstract vector fields, govern everything from radio waves to the aurora borealis. This effectiveness of mathematics in physics goes far beyond mere convenience or coincidence. Time and again, mathematical theories developed for purely abstract reasons with no thought of practical application later turn out to describe fundamental features of physical reality with extraordinary accuracy. Non-Euclidean geometry, invented by mathematicians exploring the logical consequences of denying Euclid's parallel postulate, became essential for understanding space-time curvature in general relativity. Group theory, developed to study abstract algebraic structures, proved crucial for organizing the standard model of particle physics. Even more mysterious is mathematics' predictive power. Mathematical equations don't just describe what we already know about the universe, they predict phenomena that haven't yet been observed. Einstein's field equations predicted the existence of black holes decades before any were discovered. Dirac's equation predicted the existence of antimatter before positrons were detected in cosmic rays. The mathematical formalism of quantum mechanics predicted quantum entanglement, a phenomenon so strange that Einstein called it spooky action at a distance. Wigner found this mathematical effectiveness so puzzling that he called it a miracle and suggested that we neither understand nor deserve it. But what if the effectiveness of mathematics isn't mysterious at all? What if there's a simple reason why mathematical relationships govern physical reality with such precision? MIT physicist Max Tegmark has proposed one of the most radical answers to this question ever seriously considered by a scientist. According to Tegmark's mathematical universe hypothesis, mathematics doesn't just describe physical reality, mathematics is physical reality. The universe isn't just mathematical in its behavior, it literally is a mathematical structure, existing as a pattern of abstract relationships in a realm of pure mathematical truth. Tegmark's hypothesis represents the logical extreme of mathematical thinking about physics. If the universe behaves mathematically, and if mathematics can predict physical phenomena with perfect accuracy, then perhaps there's no meaningful distinction between mathematical truth and physical existence. Numbers, equations, and geometric relationships wouldn't just describe reality, they would be reality, manifesting as the particles, forces, and fields that make up the cosmos. This idea might seem absurdly abstract, but it has concrete implications that can be tested against observation. If the mathematical universe hypothesis is correct, then we should expect the laws of physics to be not just mathematical but maximally mathematical. They should exhibit the kinds of symmetries, elegance, and mathematical beauty that characterize the most profound mathematical truths. And indeed, this is exactly what we observe. The fundamental equations of physics are remarkably elegant and symmetrical. Einstein's field equations can be written in just a few lines, yet they govern the behavior of the entire cosmos. The standard model of particle physics, despite its complexity, exhibits deep symmetries that connect seemingly unrelated phenomena. String theory, our most ambitious attempt to unify all of physics, is based on mathematical structures of extraordinary beauty and complexity. But Tegmark's hypothesis goes even further. If mathematics is reality, then every mathematically consistent structure should correspond to some physical universe. There wouldn't be just one mathematical structure manifesting as our observed cosmos. There would be infinitely many mathematical structures, each corresponding to a different possible universe with its own laws of physics, dimensions, and properties. This mathematical multiverse would be even more vast and diverse than the multiverse predicted by eternal inflation theory. It would contain not just universes with different values of physical constants, but universes with entirely different mathematical structures. There would be universes with different numbers of spatial dimensions, different types of particles, different forms of logic, and different mathematical relationships governing their evolution. Some of these mathematical universes would be simple and elegant, governed by basic arithmetic or elementary geometry. Others would be incredibly complex, involving mathematical structures so sophisticated that they're beyond current human understanding. Still others might be based on forms of mathematics that haven't yet been discovered or that operate according to logical principles completely different from those familiar to us. In this mathematical multiverse, our observed universe would be just one particular mathematical structure among infinitely many others. We observe this particular structure not because it's special or unique, but because it's the one that contains mathematical patterns complex enough to support the existence of conscious observers like ourselves. This provides a natural explanation for the apparent fine-tuning of physical constants without invoking design or supernatural intervention. The constants aren't fine-tuned by some external agent, they're simply features of the particular mathematical structure we happen to inhabit. In mathematical universes where these constants had different values, different types of complexity might emerge, or perhaps no complexity at all. But Tegmark's hypothesis raises profound questions about the nature of consciousness and subjective experience. If we are mathematical structures embedded within larger mathematical structures, what creates the sense of being a conscious observer? Why do we experience this particular mathematical universe rather than any of the infinitely many others? What determines which mathematical patterns correspond to conscious beings? These questions push us into some of the deepest puzzles in philosophy of mind. Consciousness seems to involve something more than just mathematical relationships. It involves subjective experience, the feeling of what it's like to be aware. How can purely abstract mathematical structures give rise to the vivid, qualitative experiences that characterize conscious life? One possibility is that consciousness is itself a form of information processing, and that sufficiently complex information processing systems naturally develop subjective experience. If the mathematical universe hypothesis is correct, then conscious beings would be particular types of mathematical patterns, self-referential structures capable of modeling themselves and their environment. This information theoretic view of consciousness aligns with developments in computer science and artificial intelligence. As we create increasingly sophisticated AI systems, we're beginning to understand how complex information processing can give rise to behaviors that appear intelligent and even creative. Perhaps consciousness is simply what complex information processing feels like from the inside. But this raises another profound question. If consciousness is just information processing, and if information processing can be implemented mathematically, then could the entire universe be understood as a vast information processing system? Could the cosmos literally be computing something? This computational view of the universe has gained support from several directions. Digital physics proposes that space-time itself might be discrete rather than continuous, made up of tiny pixels of space and time like a cosmic computer simulation. Quantum mechanics involves information processing at its most fundamental level, with measurement and observation playing crucial roles in determining physical outcomes. Even black holes, according to recent theories, can be understood as information processing systems that store and manipulate vast amounts of data. If the universe is computational, then its evolution over time would represent the execution of some inconceivably complex program. The Big Bang would be like initialization, setting up the initial conditions and parameters. The laws of physics would be the algorithms that govern how the computation proceeds. The emergence of structure and complexity would represent the gradual unfolding of the computational process. But what would such a cosmic computer be computing? One possibility is that it's simulating its own evolution, engaging in a kind of self-modeling where the universe calculates what it should look like at each moment based on its current state and governing laws. This would make the universe self-referential in the deepest possible sense, existing as a mathematical structure that computes its own existence. Another possibility is that the cosmic computation has some objective or purpose that we can't yet comprehend. Perhaps the universe is solving some vast optimization problem, exploring different possible configurations to find ones that maximize certain mathematical properties like complexity, beauty, or information content. Or perhaps the computation is completely open-ended, with no predetermined goal or final state. The universe might be engaged in pure exploration, generating new patterns and possibilities through the ongoing process of cosmic evolution. In this view, galaxies, stars, planets, and living beings would all be aspects of the universe's creative computation, manifestations of its capacity for generating novel and complex structures. This computational perspective suggests a new way of thinking about cosmic origins and the question of what came before the Big Bang. If the universe is fundamentally computational, then its creation might have been more like the beginning of a calculation than a physical event. The initial moment wouldn't be when matter and energy came into existence, but when the cosmic computation began executing. This raises intriguing questions about the nature of the computational substrate that supports the universe's existence. What is the cosmic computer made of? What powers it? How does it maintain its operation across cosmic time? These questions might seem like they just push the mystery back one level, but they also suggest new ways of approaching fundamental problems in physics and cosmology. Some physicists have proposed that the universe might be computing on its own quantum vacuum, using the fluctuations and interactions of virtual particles as a kind of natural computational medium. In this view, the quantum foam that fills empty space wouldn't be just a byproduct of quantum field theory, it would be the hardware on which the cosmos runs its cosmic software. Others have suggested that the universe might be computing using the fabric of space-time itself. Just as modern computers use the flow of electrons through silicon to perform calculations, the cosmic computer might use the curvature of space-time and the propagation of gravitational waves to process cosmic information. But perhaps the most radical possibility is that the universe is computing using pure mathematics itself. In this view, mathematical relationships wouldn't just describe the computational process, they would be the computational process existing as abstract calculations in some realm of pure mathematical truth. This brings us back to Tegmark's mathematical universe hypothesis, but with a computational twist. Perhaps reality consists of mathematical structures that are actively computing their own existence, self-referential patterns that exist precisely because they can model and predict their own behavior. Such self-computing mathematical structures would be remarkably stable and self-maintaining. They would exist not because some external agent created them, but because they're mathematically consistent and self-generating. Like strange loops in logic or self-referential statements in language, they would exist by virtue of their own internal coherence and computational completeness. This perspective suggests that the question, what came before the Big Bang, might be fundamentally misguided. If the universe is a self-computing mathematical structure, then it exists timelessly in the realm of mathematical truth. The appearance of temporal evolution, the sense that the universe has a history, would be generated by the computational process itself, like the way a computer simulation can create the appearance of time passing even though the entire program exists simultaneously on the computer's memory. In this view, the Big Bang wouldn't be the beginning of time, but rather the beginning of the universe's computation of time. What we experience as cosmic history would be the universe running through its mathematical self-description, generating the appearance of temporal sequence through the logical unfolding of its underlying computational structure. But even this mathematical computational perspective on reality faces the fundamental question that seems to arise at every level of explanation: why does anything exist at all? Even if the universe is a mathematical structure or a computation, why do mathematical structures exist? What gives abstract patterns the power to manifest as concrete reality? Some philosophers argue that mathematical existence is simply different from physical existence, that numbers and geometric relationships exist necessarily in some Platonic realm, independently of any physical universe. In this view, mathematical objects don't need to be created or caused because they exist timelessly as abstract truths. But others question whether this distinction between mathematical and physical existence is meaningful. If mathematics can completely describe physical reality, and if physical reality behaves in perfectly mathematical ways, then perhaps there's no real difference between mathematical and physical existence. Perhaps what we call physical is just our subjective experience of being embedded within certain types of mathematical structures. This leads to a remarkable possibility. Perhaps the reason something exists rather than nothing is that existence itself is mathematically necessary. Just as mathematical truths like 2 + 2 = 4 don't require explanation because they're logically inevitable, perhaps the existence of some mathematical reality is logically inevitable. In this view, the puzzle isn't why something exists rather than nothing, but why this particular something exists rather than some other something. And that question might have an anthropic answer. We observe this particular mathematical reality because we're part of it, because it's the one that generated mathematical structures complex enough to support conscious observers like ourselves. The mathematical universe hypothesis represents perhaps the most ambitious attempt ever made to understand the nature of reality at its deepest level. It suggests that the boundary between abstract thought and concrete existence, between mathematical truth and physical reality, might be an illusion created by our limited perspective as embedded observers within one particular mathematical structure. If Tegmark is correct, then the universe is not just stranger than we imagine. It's stranger than we can imagine because our imagination itself is constrained by the particular mathematical structure we inhabit. Other mathematical universes might operate according to forms of logic and patterns of relationship that are completely incomprehensible to minds evolved within our particular cosmic context. Yet the hypothesis also offers a kind of cosmic optimism. If reality consists of all possible mathematical structures, then every coherent pattern, every beautiful relationship, every possible form of complexity in consciousness exists somewhere in the vast mathematical multiverse. Nothing that can exist fails to exist, nothing that can be thought fails to be real. This mathematical view of reality also suggests new ways of thinking about human knowledge and scientific discovery. When mathematicians discover new theorems or when physicists uncover new laws of nature, they might not be creating knowledge, but literally discovering aspects of the mathematical structures that constitute reality itself. Scientific research would be a form of cosmic archaeology, uncovering the mathematical relationships that define our particular corner of the infinite mathematical multiverse. But perhaps the most profound implication of the mathematical universe hypothesis concerns the nature of consciousness and our place in the cosmic order. If we are mathematical patterns embedded within larger mathematical patterns, then our capacity for understanding mathematics isn't just a useful tool for describing reality, it's the fundamental basis of our existence. We don't just use mathematics to understand the universe, we are mathematics understanding itself. Our consciousness, our creativity, our sense of beauty and wonder, all of these would be aspects of the mathematical structure of reality, becoming aware of its own nature and exploring its own possibilities. This brings us to yet another profound possibility that emerges from the mathematical universe hypothesis. If consciousness is what happens when mathematical structures become self-aware, and if the universe itself is a mathematical structure, then perhaps the cosmos as a whole is evolving toward consciousness. Perhaps the emergence of conscious beings like ourselves represents the universe beginning to wake up, starting to understand its own mathematical nature. In this view, the evolution of complexity from simple hydrogen atoms to living cells to conscious minds wouldn't be an accident or a byproduct of physical processes. It would be the universe developing the capacity for self-understanding, creating within itself the mathematical patterns necessary for conscious observation and contemplation. We would be the universe becoming conscious of itself, reality developing the capacity to know and appreciate its own mathematical beauty and complexity. Through our scientific investigations, our mathematical discoveries, and our philosophical reflections, the cosmos would be engaged in the profound project of self-discovery. But this cosmic awakening might be just the beginning. If consciousness can emerge from mathematical complexity, and if conscious beings can create new technologies and new forms of artificial intelligence, then the universe's capacity for self-understanding might be accelerating exponentially. We might be living at the dawn of an age when the cosmos begins to understand and modify its own mathematical foundations. Such possibilities push us toward questions that blur the boundaries between science, philosophy, and speculation about the ultimate nature and purpose of existence. They suggest that the story of cosmic origins isn't just about how the universe began, but about where it might be heading and what role conscious beings like ourselves might play in its ongoing evolution. As we stand at the threshold of an age when artificial intelligence might surpass human capabilities, when quantum computers might simulate complex systems that exceed our current understanding, and when our mathematical theories are beginning to probe the deepest foundations of reality itself, we may be approaching answers to questions that have puzzled humans since we first began to wonder about our place in the cosmos. The mathematical universe hypothesis offers a vision of reality that is both deeply mysterious and surprisingly hopeful. It suggests that we live in a cosmos that is not just vast and complex, but beautiful in the deepest possible sense. Beautiful because it is literally made of mathematical beauty, existing as pure pattern and relationship in the realm of abstract truth. Whether this vision proves correct or not, it represents a remarkable achievement of human thought, pushing the boundaries of what we can conceive about the nature of existence itself. It reminds us that the universe is under no obligation to conform to our intuitions about what is reasonable or possible, and that the truth about cosmic origins might be far stranger and more wonderful than anything we have yet imagined. But even as we contemplate the possibility that we are mathematical beings living in a mathematical universe, new questions continue to emerge. If reality is fundamentally computational or mathematical, what role does consciousness play in bringing these abstract structures to life? Are we passive observers of mathematical truth or active participants in its ongoing creation and discovery? These questions point us toward our next exploration, the nature of consciousness itself and its relationship to the cosmic processes that brought us into being. We need to understand not just how the universe creates complexity, but how complexity creates the capacity for subjective experience, self-awareness, and the profound sense of wonder that drives our quest to understand our own cosmic origins. In a small laboratory at the University of Wisconsin in 2005, neuroscientist Giulio Tononi was conducting an experiment that would challenge our most basic assumptions about consciousness and its place in the natural world. Using advanced brain imaging technology, Tononi and his colleagues were measuring the responses of sleeping and anesthetized patients to magnetic pulses applied to different regions of their brains. What they found was remarkable. When the patients were awake and conscious, the magnetic pulses triggered complex, integrated responses that spread throughout the brain in intricate patterns. But when the same patients were unconscious, either in deep sleep or under anesthesia, the brain's response was dramatically different. The pulses triggered only local, isolated responses that failed to integrate across different brain regions. This experiment provided direct evidence for Tononi's integrated information theory of consciousness, one of the most promising scientific approaches to understanding what might be the universe's greatest mystery. According to this theory, consciousness corresponds to the amount of integrated information in a system. The more information a system can integrate across its parts, the more conscious it becomes. But Tononi's theory has implications that extend far beyond neuroscience. If consciousness really does correspond to integrated information, then it's not unique to brains or even to biological systems. Any system that can integrate information in sufficiently complex ways, whether it's a computer, a social network, or perhaps even the universe itself, could potentially be conscious. This possibility raises profound questions about the relationship between consciousness and the cosmic processes that brought us into being. Are conscious beings like ourselves accidental byproducts of cosmic evolution, or do we represent something more fundamental? Perhaps the universe developing the capacity to understand itself. The question of consciousness's place in the cosmic order touches on some of the deepest puzzles in science and philosophy. For centuries, materialist thinking has assumed that consciousness is simply what happens when matter becomes sufficiently complex and organized. According to this view, awareness is an emergent property of neural networks, no more mysterious than the way temperature emerges from molecular motion or the way weather patterns emerge from atmospheric dynamics. But consciousness seems to involve something that purely physical processes struggle to explain: subjective experience itself. It's not just that brains process information or exhibit intelligent behavior, it's that there's something it feels like to be conscious. There's a qualitative, experiential dimension to awareness that seems to go beyond anything that can be captured by purely objective physical descriptions. This is what philosopher David Chalmers calls the hard problem of consciousness. We can explain the functional aspects of consciousness, how it processes information, enables learning, guides behavior, and supports complex cognition. But we struggle to explain why there should be any subjective, experiential aspect to these processes at all. Why isn't the brain just a sophisticated biological computer processing information without any inner experience? The hard problem becomes even more mysterious when we consider consciousness's relationship to cosmic evolution. If subjective experience really is irreducible to physical processes, then how did it emerge from a universe that began with nothing but hydrogen atoms and the fundamental forces of physics? How does unconscious matter give rise to conscious minds? Some philosophers and scientists have proposed radical solutions to this puzzle. Perhaps consciousness isn't something that emerges from matter, but rather something that's fundamental to reality itself. This view, called panpsychism, suggests that all matter and energy have some form of primitive conscious experience, and that complex consciousness like ours emerges when simple conscious entities combine in appropriate ways. Panpsychism might seem outlandish, but it has a distinguished philosophical history and is being taken seriously by some contemporary thinkers. If consciousness is indeed fundamental, then its appearance in cosmic evolution wouldn't be a mysterious accident, but a natural consequence of the universe's basic properties. Conscious beings would represent the cosmos, exploring its own inherent capacity for subjective experience. But panpsychism raises its own puzzles. If electrons and quarks are conscious, why don't we notice their consciousness? How do billions of micro-conscious entities combine to create a unified conscious experience? What determines which combinations of matter give rise to consciousness and which don't? An alternative approach suggests that consciousness might be an emergent property that arises when information processing reaches sufficient complexity and integration. This emergence wouldn't be mysterious in the way that panpsychists suggest consciousness is fundamental, but it would represent a genuine phase transition, a moment when quantitative complexity gives rise to qualitatively new properties. We see such phase transitions throughout nature. When hydrogen and oxygen combine in the right proportions, they create water, a substance with properties like wetness and fluidity that couldn't be predicted from knowledge of the component atoms alone. When neurons connect in sufficiently complex networks, they might create consciousness, an emergent property that's genuinely novel but arises naturally from the underlying physical processes. This emergentist view of consciousness aligns with what we observe about cosmic evolution more generally. The universe has been creating increasingly complex structures throughout its history, each with emergent properties that weren't present at simpler levels of organization. Atomic nuclei have properties that isolated protons and neutrons don't possess. Molecules have properties that individual atoms lack. Living cells exhibit behaviors that non-living chemical systems can't achieve. Perhaps consciousness represents the latest and most remarkable example of cosmic emergence, the point at which organized matter develops the capacity for subjective experience and self-awareness. From this perspective, the evolution of conscious beings like ourselves wouldn't be an accident, but a natural outcome of the universe's tendency toward greater complexity and organization. But this raises profound questions about the direction and purpose of cosmic evolution. If the universe really does have a tendency to generate increasing complexity, and if this tendency leads naturally to the emergence of consciousness, then perhaps conscious beings represent something the cosmos is trying to become. This teleological view of cosmic evolution, the idea that the universe has inherent goals or directions, has fallen out of favor in modern science. The mechanisms of evolution through natural selection seem to explain the complexity of life without invoking any cosmic purpose or design. Physical processes appear to operate mechanistically according to mathematical laws, without any goal-directed behavior. But some features of cosmic evolution do seem to show directional trends that are difficult to explain through purely random processes. The universe has evolved from simple hydrogen and helium atoms to incredibly complex structures like living cells, ecosystems, and conscious minds. This progression toward greater complexity and information processing capability might reflect deeper principles that we don't yet understand. Moreover, the fine-tuning of physical constants that allows complex structures to exist at all raises questions about whether the universe really is as purposeless as materialist thinking suggests. The strength of gravity, the mass of the electron, the rate of cosmic expansion, and dozens of other parameters seem to be precisely adjusted to allow stars to shine, planets to form, and chemistry to work in ways that support complex organization. If any of these constants were significantly different, the universe would be a much simpler and less interesting place. Stars might never form, or they might burn out too quickly for planets to develop. Atomic nuclei might be unstable, or chemical bonds might be too weak to support complex molecules. The emergence of life and consciousness would be impossible. This apparent fine-tuning has led some scientists and philosophers to propose that consciousness might not be an accidental byproduct of cosmic evolution, but rather its fundamental purpose. According to this view, the universe exists in order to create conscious beings capable of understanding and appreciating their own existence. Such anthropic reasoning suggests that conscious observers aren't just passive products of cosmic processes, but active participants in bringing reality into being. Some interpretations of quantum mechanics support this view, suggesting that conscious observation plays a fundamental role in determining physical outcomes. The universe might literally require conscious beings to collapse quantum wave functions and give definite properties to physical systems. If this interpretation is correct, then consciousness wouldn't just be something the universe creates, it would be something the universe needs to exist in definite form. We wouldn't be accidental observers of cosmic history, but essential participants in its ongoing creation. But even if consciousness doesn't play such a direct role in quantum mechanics, it clearly plays a crucial role in cosmic evolution more generally. Through science, technology, and cultural development, conscious beings are beginning to shape the future of cosmic evolution in unprecedented ways. We're modifying our own planet's atmosphere, designing new forms of life through genetic engineering, and beginning to explore and potentially colonize other worlds. In a sense, consciousness represents the universe developing the capacity to understand and modify its own evolution. Through conscious beings like ourselves, the cosmos is becoming self-aware and self-directing. We're not just products of cosmic evolution, we're agents of its future development. This perspective suggests that the emergence of consciousness might represent a phase transition in cosmic evolution as significant as the formation of the first atoms or the ignition of the first stars. For the first time in the universe's 13.8 billion-year history, matter has organized itself in ways that allow for self-reflection, intentional action, and conscious choice about the future direction of cosmic development. But consciousness also brings with it the capacity for suffering, conflict, and potentially destructive behavior. Nuclear weapons, climate change, and ecological destruction demonstrate that conscious beings can threaten not just their own survival, but the survival of entire ecosystems and perhaps even planets. This raises profound questions about the ultimate value and purpose of consciousness in cosmic evolution. If awareness inevitably leads to the capacity for both creation and destruction, both understanding and ignorance, both love and hatred, then is consciousness really a positive development in cosmic history? Some philosophers argue that consciousness is valuable precisely because it allows for the possibility of meaning, purpose, and moral choice. A universe without consciousness would be neither good nor bad. It would simply exist without any capacity for evaluation or judgment. Only conscious beings can find the universe beautiful, terrible, meaningful, or absurd. From this perspective, the emergence of consciousness represents the universe developing the capacity for self-evaluation and moral choice. Through conscious beings, the cosmos can reflect on its own value and work toward goals that transcend mere physical survival or reproduction. But this moral dimension of consciousness also highlights its mysterious nature. Why should conscious beings care about anything beyond their own immediate self-interest? Why do we find some things beautiful and others ugly, some actions right and others wrong? Where do values and purposes come from in a universe that began with nothing but matter, energy, and physical law? These questions push beyond the boundaries of current scientific understanding into realms where science, philosophy, and perhaps theology converge. The emergence of consciousness from unconscious matter is mysterious enough, but the emergence of moral consciousness, beings who can conceive of purposes beyond their own existence, is even more puzzling. Some researchers have proposed that consciousness and moral awareness might be connected to the universe's fundamental structure in ways we don't yet understand. If reality is fundamentally mathematical or informational, as some theories suggest, then perhaps consciousness represents the universe developing the capacity to appreciate its own mathematical beauty and complexity. In this view, our sense of wonder at cosmic beauty, our drive to understand the mathematical laws that govern reality, and our capacity for moral choice would all be aspects of the universe's self-appreciation and self-direction. Through conscious beings, the cosmos would be engaged in the profound project of understanding and valuing its own existence. But consciousness might also represent something even more remarkable, the universe developing the capacity to transcend its own limitations. Through imagination, creativity, and technological development, conscious beings can conceive of possibilities that don't yet exist and work to bring them into being. We can imagine forms of beauty that have never existed, develop new technologies that extend our capabilities beyond biological limitations, and explore philosophical and scientific questions that push the boundaries of current understanding. In a sense, consciousness allows the universe to dream about its own future and work toward realizing those dreams. This creative capacity of consciousness raises intriguing questions about the future of cosmic evolution. If conscious beings can transcend their biological limitations through technology, if they can explore and potentially modify the fundamental laws of physics, and if they can conceive of forms of existence that transcend current understanding, then the emergence of consciousness might represent the beginning of an entirely new phase of cosmic development. Some futurists envision a time when conscious beings might develop the ability to create new forms of matter and energy, manipulate the fabric of space-time itself, or even create new universes with different physical laws. If such capabilities are possible, then consciousness would represent not just the universe becoming self-aware, but the cosmos developing godlike powers of creation and transformation. But these speculative possibilities also highlight the responsibility that comes with consciousness. If conscious beings really do have the potential to shape the future of cosmic evolution, then our choices and actions take on cosmic significance. We're not just individuals pursuing our own goals, we're agents of the universe's ongoing development, participants in a cosmic story whose outcome is still being determined. This responsibility extends to our quest to understand cosmic origins itself. Through science, philosophy, and contemplation, conscious beings are literally engaged in the universe's effort to understand its own nature and history. Our investigations into what came before the Big Bang, our theories about the ultimate nature of reality, and our search for meaning and purpose in existence are all aspects of the cosmos's self-investigation. From this perspective, the questions we've been exploring throughout this journey, from cosmic expansion to quantum mechanics to mathematical reality, aren't just academic exercises. They're part of the universe's fundamental project of self-discovery, the cosmos coming to understand its own deepest nature through the consciousness it has created. But consciousness also brings with it the recognition of our own limitations and mortality. Individual conscious beings live for only a brief moment in cosmic time, and even our entire species may represent only a fleeting phase in cosmic evolution. How can finite, mortal beings participate meaningfully in cosmic processes that unfold over billions of years? Perhaps the answer lies in the cumulative nature of conscious understanding. Each generation of conscious beings builds on the knowledge and wisdom of previous generations, creating a growing body of understanding that transcends individual mortality. Through culture, education, and the preservation of knowledge, consciousness creates a form of collective memory that allows insights to accumulate over time. In this sense, human civilization represents the universe's developing memory system, a way for the cosmos to accumulate and preserve understanding of its own nature across time. Our libraries, universities, and scientific institutions are literally cosmic memory banks, storing the universe's growing self-knowledge for future generations of conscious beings to build upon. But consciousness also raises questions about our relationship to other possible conscious beings elsewhere in the cosmos. If consciousness represents a natural outcome of cosmic evolution, then it's likely that conscious beings have emerged on countless other worlds throughout the universe. How do we relate to this vast community of cosmic consciousness that we're only beginning to imagine? The search for extraterrestrial intelligence represents more than just scientific curiosity. It's an attempt to connect with other aspects of the universe's self-awareness. Discovering other conscious beings would confirm that consciousness is indeed a natural and perhaps inevitable outcome of cosmic evolution. It would also raise profound questions about the diversity of possible forms of consciousness and the various ways the universe might understand itself. But whether we're alone in the cosmos or part of a vast community of conscious beings, our existence as aware, questioning, creative entities represents something remarkable in the history of the universe. Through consciousness, the cosmos has developed the capacity to wonder about its own origins, to find beauty in its own complexity, and to work toward futures that transcend its current limitations. As we stand at the beginning of the 21st century, with our understanding of cosmic origins deeper than ever before, but with profound mysteries still unsolved, consciousness continues to drive our quest for understanding. We're not satisfied with accepting reality as we find it. We want to understand why it exists, how it works, and what it might become. This drive to understand and transcend represents perhaps the most remarkable feature of conscious beings. We're not content to simply exist. We want to exist meaningfully, purposefully, in full awareness of our place in the cosmic story. Through science, philosophy, art, and spiritual exploration, we're engaged in the ongoing project of making existence meaningful and beautiful. But consciousness also confronts us with ultimate questions that may have no final answers. Why does anything exist at all? What is the ultimate nature of reality? Do our lives and choices have cosmic significance, or are we just fleeting accidents in an indifferent universe? These questions may be unanswerable in any final sense, but they continue to drive conscious exploration and creativity. Perhaps the questions themselves are more important than any answers we might find. Perhaps consciousness exists not to solve the mystery of existence, but to celebrate it, to explore it with wonder and creativity, to find meaning in the very act of questioning. From this perspective, our quest to understand what came before the Big Bang, our exploration of the deepest nature of reality, and our search for meaning and purpose in existence are all expressions of consciousness fulfilling its cosmic role. We are the universe, asking questions about itself, reality coming to understand its own nature, existence celebrating its own mystery and beauty. Whether consciousness represents the universe's ultimate purpose or simply its most remarkable accident, it has become the driving force behind cosmic evolution's next phase. Through conscious beings, the cosmos continues to explore its own possibilities, to transcend its current limitations, and to work toward futures that we can barely imagine. The story of consciousness in cosmic evolution is still being written, and we are both its authors and its protagonists. Where this story leads depends in part on the choices we make, the questions we ask, and the dreams we pursue. As conscious participants in the cosmic story, we have the extraordinary opportunity and responsibility to help shape the universe's ongoing journey of self-discovery and self-creation. But as we contemplate these profound questions about consciousness and cosmic purpose, we must also confront the ultimate mystery that has driven our entire exploration, the question of why anything exists at all. Even if consciousness represents the universe's way of understanding itself, even if reality is mathematical or computational in nature, even if existence emerges naturally from quantum processes, we still face the fundamental puzzle of existence itself. This brings us to our final exploration, the ultimate questions about existence, meaning, and the possibility that some mysteries may be meant to remain mysterious. We must grapple with the limits of human understanding and the possibility that the deepest truths about reality may forever remain beyond our grasp, while still celebrating the remarkable journey that has brought us to the edge of these cosmic mysteries. In the summer of 1969, as humanity took its first steps on the lunar surface, philosopher Thomas Nagel was writing an essay that would challenge our understanding of knowledge itself. In What Is It Like to Be a Bat? Nagel argued that there are fundamental aspects of reality that might be forever beyond human comprehension, not because our instruments aren't sensitive enough or our theories aren't sophisticated enough, but because the nature of conscious experience itself places absolute limits on what any finite mind can understand. Nagel's argument was deceptively simple. A bat experiences the world through echolocation. It navigates by emitting high-frequency sounds and interpreting the returning echoes to build a three-dimensional map of its environment. This creates a form of consciousness completely alien to human experience. While we can study the physics of sound waves and the neurology of bat brains, we can never know what it actually feels like to experience the world through echolocation. This limitation isn't temporary or technical, it's fundamental. No amount of scientific progress can give us direct access to the subjective experience of being a bat, because conscious experience is inherently private and first personal. We can understand how echolocation works, but we can't experience what it's like to echolocate. If this is true for something as relatively simple as bat consciousness, Nagel argued, how much more might it be true for the deepest questions about reality itself? Perhaps there are aspects of existence that are forever beyond human understanding, not because we lack the right instruments or theories, but because the nature of reality transcends what any finite, embodied consciousness can comprehend. As we reach the end of our journey through the deepest questions about cosmic origins, Nagel's insight becomes increasingly relevant. We've traced the universe's history from cosmic expansion through the Big Bang to inflation theory, from quantum mechanics to mathematical reality, from the emergence of consciousness to questions about cosmic purpose. At each stage, we found that answering one question leads to deeper questions, that solving one mystery reveals greater mysteries beneath. Perhaps this infinite regress isn't a temporary frustration to be overcome by future scientific progress. Perhaps it's a fundamental feature of reality itself, an indication that existence is more mysterious and wonderful than any finite mind can ever fully comprehend. Consider the progression of our understanding. When Edwin Hubble discovered cosmic expansion, it seemed like the ultimate revelation about the universe's nature. But this discovery immediately raised new questions. What caused the expansion? What existed before it began? How long will it continue? When the cosmic microwave background was discovered, confirming the Big Bang theory, it seemed like we had found the ultimate evidence for cosmic origins. But this discovery revealed new puzzles. Why was the early universe so uniform? Why was its geometry so precisely flat? Where were the exotic particles that theories predicted? When inflation theory was developed to solve these problems, it seemed like the final piece of the cosmological puzzle. But inflation led to even more radical possibilities. Eternal inflation, the multiverse, the idea that our Big Bang was just one bubble among infinitely many others, each with its own physics and history. When quantum mechanics offered explanations for how something could emerge from nothing, it seemed like we had finally reached the bottom of the explanatory chain. But quantum theories raise their own profound questions. Why do quantum fields exist? What gives mathematical structures the power to manifest as physical reality? How does subjective experience relate to objective physical processes? At each stage, the horizon of the unknown recedes before us. Every answer illuminates new questions, every solution reveals new problems, every mystery solved exposes deeper mysteries waiting to be explored. We seem to be caught in an infinite regression where complete understanding always remains just beyond our grasp. But perhaps this is not a failure of human knowledge. Perhaps it's a revelation about the nature of reality itself. Perhaps existence is inherently inexhaustible, containing infinite depths of complexity and mystery that no finite intelligence could ever completely fathom. Perhaps the universe is not just vast in space and time, but infinite in the richness of its structure and the profundity of its secrets. This would be a strange and wonderful cosmos indeed, one where every scientific discovery, every philosophical insight, every artistic creation opens new doors to further exploration. It would be a reality perfectly suited to conscious beings like ourselves, who seem to find meaning and purpose not in final answers, but in the endless quest for understanding. From this perspective, the question, what came before the Big Bang, might not be a puzzle waiting to be solved, but an invitation to exploration that will never end. Each theory we develop, whether it involves inflation, quantum fluctuations, mathematical structures, or something we haven't yet imagined, will inevitably lead to new questions about what makes that theory possible and what lies beyond its explanatory reach. But this infinite mystery is not a cause for despair or resignation. Instead, it suggests that we live in a universe of inexhaustible wonder, where consciousness will always have new frontiers to explore and new forms of beauty and truth to discover. If reality is fundamentally mysterious, then the quest for understanding becomes not just a means to an end, but an end in itself. This perspective transforms how we think about the limitations of human knowledge. Rather than seeing these limitations as failures or frustrations, we can understand them as necessary features of finite consciousness encountering infinite reality. We're not meant to understand everything. We're meant to participate in the ongoing exploration of an inexhaustibly rich and complex cosmos. But even as we acknowledge the limits of human understanding, we must also celebrate how far we've come. In just a few centuries of systematic scientific investigation, we've traced the universe's history back to its first fraction of a second. We've discovered that space and time are dynamic and malleable, that matter and energy can be created from quantum fluctuations, that reality might consist of multiple dimensions and parallel universes. We've learned that consciousness might be fundamental to the nature of reality, that mathematical beauty might be more than aesthetic preference, but a guide to cosmic truth, that the emergence of minds capable of understanding their own existence might represent the universe becoming self-aware. These insights represent an extraordinary achievement of human thought and observation. Moreover, our quest to understand cosmic origins has revealed something profound about the nature of conscious beings like ourselves. We are not content to simply exist. We want to understand existence. We're not satisfied with accepting reality as we find it. We want to know why it is the way it is and what it might become. This drive to understand and transcend current limitations seems to be fundamental to consciousness itself. In a sense, we are the universe asking questions about itself. Through our scientific investigations, our philosophical reflections, and our artistic expressions, the cosmos is engaged in the remarkable project of self-understanding. We represent reality becoming conscious of its own nature and exploring its own possibilities. This gives our existence a kind of cosmic significance that transcends our individual mortality and our species' brief tenure on Earth. Even if human civilization is just a fleeting moment in cosmic history, the consciousness we represent, the universe's capacity for self-awareness and self-questioning, might be permanent features of cosmic evolution. If consciousness is indeed a natural outcome of complexity under the right conditions, then conscious beings like ourselves have probably emerged countless times throughout cosmic history on planets orbiting distant stars. Each emergence of consciousness represents the universe developing new ways of understanding itself, new perspectives on its own nature and possibilities. From this cosmic perspective, our quest to understand what came before the Big Bang is part of an ongoing conversation that conscious beings throughout the universe are having with existence itself. We're participating in a cosmic dialogue that began with the first conscious thoughts and will continue as long as consciousness persists anywhere in the cosmos. But consciousness also brings with it the recognition of our own finitude and mortality. Individual conscious beings live for only a brief moment in cosmic time, and even our entire species may represent only a transient phase in cosmic evolution. How can finite beings meaningfully participate in infinite processes of cosmic exploration? Perhaps the answer lies in the cumulative and collaborative nature of conscious understanding. Each generation of conscious beings builds on the insights of previous generations, creating a growing body of knowledge that transcends individual limitations. Through culture, education, and the preservation of ideas, consciousness creates forms of collective memory and understanding that can persist far longer than individual lives. In this sense, our scientific theories, philosophical insights, and artistic creations are contributions to a cosmic library of understanding that conscious beings throughout the universe are collectively building. Each discovery we make, each question we ask, each new perspective we develop adds to this growing repository of cosmic self-knowledge. But consciousness also faces the possibility of its own extinction. Nuclear weapons, climate change, and other technological risks suggest that consciousness, despite its cosmic significance, remains fragile and vulnerable. The emergence of conscious beings like ourselves might be rare and precious, representing something that the universe achieves only under very special conditions and only after billions of years of cosmic evolution. This possibility gives our current moment in cosmic history special urgency and importance. We might be living at a critical juncture when consciousness either establishes itself as a permanent feature of cosmic evolution or proves to be just another temporary phase in the universe's development. If consciousness is to persist and flourish, it will likely need to transcend its current biological limitations. Through artificial intelligence, genetic engineering, and other emerging technologies, conscious beings might develop capabilities that far exceed those of their biological ancestors. Future forms of consciousness might be able to explore cosmic mysteries that are currently beyond our reach, to survive conditions that would destroy biological life, and to persist across cosmic timescales that dwarf current lifespans. Such transcendent consciousness might eventually develop the ability to manipulate the fundamental structures of reality itself, to create new forms of matter and energy, to modify the constants of physics, perhaps even to create new universes with different laws and possibilities. If such capabilities are achievable, then consciousness would represent not just the universe becoming self-aware, but the cosmos developing godlike powers of creation and transformation. But even transcendent consciousness would likely face the same fundamental mystery that confronts us today, the question of why anything exists at all. No matter how sophisticated our understanding becomes, no matter how powerful our capabilities grow, we will always face the ultimate puzzle of existence itself. Why is there something rather than nothing? Why does reality take the particular form it does rather than some other form or no form at all? Why do the laws of physics exist, and why do they take the mathematical structures they do? These questions might remain mysterious no matter how far consciousness evolves and how deep our understanding becomes. Perhaps this ultimate mystery is not a problem to be solved, but the fundamental condition of existence itself. Perhaps being itself is inexplicably mysterious, and any conscious exploration of reality will ultimately encounter this irreducible mystery at its core. If this is true, then the deepest truth about existence might be that it is fundamentally inexplicable, not because our knowledge is incomplete, but because explicability itself requires a context of prior assumptions and principles, and there can be no such context for existence as a whole. The universe might be self-grounding and self-explanatory, or it might be gratuitously mysterious, but it cannot be explained in terms of something more fundamental because there is nothing more fundamental than existence itself. This doesn't mean that scientific investigation and philosophical reflection are pointless. Even if ultimate questions remain unanswerable, the process of exploration itself creates meaning and value. Through investigation, we discover remarkable truths about the nature of reality. We develop our capacities for understanding and appreciation, and we participate in the cosmic process of self-exploration. Moreover, the journey of exploration transforms us as explorers. Through science and philosophy, we develop more sophisticated ways of thinking, more refined capacities for observation and reasoning, and deeper appreciation for the complexity and beauty of existence. We become more conscious, more aware, more capable of participating meaningfully in the ongoing cosmic story. Perhaps this transformation of consciousness through exploration is itself the point of the exercise. Perhaps the universe doesn't exist to be completely understood, but to provide an inexhaustible context for conscious growth, exploration, and creative expression. From this perspective, the questions are more important than the answers because the questions drive the process of conscious development. But as we contemplate these ultimate questions and possible limitations of understanding, we must also acknowledge the extraordinary journey that has brought us to this point. Starting with simple observations of stellar positions and galactic redshifts, we've developed theories that probe the deepest foundations of reality itself. We've learned that the familiar world of everyday experience is just a tiny slice of a much larger and stranger reality. Space and time are not fixed backdrops, but dynamic entities that can be curved, stretched, and perhaps even created. Matter and energy are interconvertible and can emerge from apparently empty quantum fields. The universe we observe might be one bubble in an infinite multiverse, one calculation in a cosmic computation, one mathematical structure in an infinite realm of abstract truth. These discoveries have expanded our conception of what's possible and challenged our most basic assumptions about the nature of existence. They've shown us that reality is far more flexible, creative, and mysterious than common sense suggests. They've opened our minds to possibilities that previous generations couldn't have imagined. But perhaps most importantly, our exploration of cosmic origins has revealed something profound about ourselves and our place in the cosmic order. We are not passive observers of an independent reality, but active participants in its ongoing evolution and self-discovery. Through consciousness, the universe has developed the capacity to wonder about its own existence, to find beauty in its own complexity, and to work toward futures that transcend current limitations. This participatory role gives our existence meaning that extends far beyond our individual lives and immediate concerns. We are agents of cosmic evolution, representatives of the universe's drive toward greater complexity, understanding, and self-awareness. Through our quest to understand cosmic origins, we participate in reality's ongoing project of self-exploration and self-creation. Whether we ultimately solve the mystery of what came before the Big Bang or discover that this question has no final answer, the quest itself represents something remarkable about the nature of conscious existence. We are the universe asking questions about itself, reality contemplating its own mystery, existence marveling at its own possibility. This capacity for wonder, questioning, and exploration might be the most important thing that has emerged in cosmic evolution since the Big Bang itself. Through consciousness, the cosmos has transcended mere physical existence to become something that can appreciate beauty, seek truth, create meaning, and imagine possibilities that don't yet exist. As we look toward the future of cosmic exploration, we can be confident that new discoveries await us. More powerful telescopes will peer deeper into space and further back in time, potentially revealing new aspects of cosmic origins. More sophisticated theories will probe the interface between quantum mechanics and gravity, perhaps solving the puzzle of how something emerges from nothing. More advanced forms of consciousness, whether biological, artificial, or something we can't yet imagine, will explore questions that are currently beyond our reach. But whatever we discover, we can expect that new mysteries will emerge to replace the ones we solve. The horizon of the unknown will continue to recede before us, always revealing new frontiers for exploration. If reality is fundamentally inexhaustible, then consciousness will always have new territories to explore and new forms of understanding to develop. This might be the deepest truth about cosmic origins, not that the universe had a particular beginning at a specific moment in time, but that it represents an ongoing process of creative emergence where new possibilities are constantly arising. From this perspective, the Big Bang was not just the start of cosmic expansion, but the beginning of an eternal process of cosmic self-creation and self-discovery. We are part of this process, participants in the universe's ongoing journey of exploration and creativity. Through our quest to understand cosmic origins, we contribute to reality's endless project of coming to know itself. Whether we find final answers or encounter eternal mysteries, we participate in something larger and more wonderful than ourselves. The question, what came before the Big Bang, has taken us on an extraordinary journey through the deepest insights of modern science and philosophy. We've explored cosmic expansion, the discovery of the cosmic microwave background, inflation theory and the multiverse, quantum mechanics and virtual particles, mathematical reality and computational universes, the emergence of consciousness and questions of cosmic purpose. At each stage, we found that answering one question opens up new questions, that solving one mystery reveals deeper mysteries, that understanding one aspect of reality illuminates how much we don't yet understand. This infinite regress might seem frustrating, but it's actually the most hopeful possible outcome. If reality is inexhaustibly mysterious, then consciousness will always have new frontiers to explore. If existence is fundamentally creative and self-transcending, then conscious beings will always have opportunities to grow, develop, and participate in cosmic evolution. If the universe is engaged in an eternal process of self-discovery, then our quest for understanding cosmic origins is part of a larger story that will continue as long as consciousness persists anywhere in the cosmos. We stand today at a remarkable moment in this ongoing story. For the first time in cosmic history, conscious beings have developed the capability to probe their own ultimate origins, to ask questions about the nature of existence itself, to participate knowingly in cosmic evolution. We are the universe becoming conscious of itself, reality developing the capacity for self-understanding and self-direction. What comes next in this cosmic story depends partly on us. Through our choices about how to pursue knowledge, how to develop technology, how to organize society, and how to relate to the cosmos and each other, we help shape the future of consciousness and its role in cosmic evolution. But regardless of what particular discoveries await us, we can be confident that the fundamental quest will continue. Consciousness will keep asking questions about existence, reality will keep revealing new aspects of its mystery, and the cosmic conversation between mind and cosmos will continue to unfold in ways we cannot yet imagine. The Big Bang may have marked the beginning of our particular cosmic epoch, but it also marked the beginning of a process that has no end, the universe's endless journey of self-discovery through the consciousness it creates. We are both products of this journey and active participants in its continuation. In asking what came before the Big Bang, we join an eternal conversation between consciousness and cosmos, between the known and the unknown, between the possible and the actual. This conversation is not just the pursuit of abstract knowledge, but the living expression of what it means to be conscious beings in a universe that has somehow given rise to conscious beings capable of questioning their own existence. Whatever ultimate truths await discovery, whatever final mysteries remain forever beyond our grasp, we can find meaning and purpose in this ongoing exploration itself. We are the universe's way of questioning its own nature, celebrating its own beauty, and working toward possibilities not yet realized. The story that began 13.8 billion years ago with the Big Bang continues today in every question we ask, every theory we develop, every moment of wonder we experience in contemplating the vast mystery of existence. We are the latest chapter in an epic tale of cosmic evolution, and we are actively writing that chapter through our quest to understand our place in the cosmic order. What came before the Big Bang? Perhaps the question itself, the capacity for questioning that allows conscious beings to probe the deepest mysteries of existence. Perhaps what came before was the potential for consciousness, the possibility that the universe might someday become aware of its own existence and begin the eternal quest to understand its own nature. If so, then we represent not just products of cosmic history, but the universe's answer to its own deepest question: can reality come to know itself? Through our existence and our quest for understanding, the cosmos demonstrates that yes, reality can indeed become self-aware, self-questioning, and self-transcending. We are the universe's proof that consciousness is possible, that beauty can be appreciated, that truth can be sought and sometimes found, that meaning can emerge from mystery. In our questioning, we keep the cosmic conversation alive. In our wondering, we embody the universe's capacity for wonder. In our searching, we represent reality's endless quest to understand itself. The journey continues, the questions multiply, the mystery deepens. And in that deepening mystery, consciousness finds its eternal home and its infinite purpose. We are explorers in an inexhaustible cosmos, questioners of inexhaustible questions, participants in a cosmic story that has no end because its mystery and beauty can never be fully exhausted. What came before the Big Bang? Perhaps the same thing that comes after it, the eternal mystery of existence itself, forever creating new possibilities for conscious exploration and cosmic self-discovery. In that mystery, we find not limitation, but liberation. The freedom to continue questioning, exploring, and marveling at the extraordinary fact that anything exists at all, and that within that existence, consciousness has emerged to contemplate its own cosmic origins and infinite future.